Right, and Justin, I think I'm setting you up to fail here, because you see this question from January 2024, it's not explicitly stated in the syllabus. So Justin, and you remember Fleming's left hand rule,
Yeah,
right? So your thumb is thrust, the second finger is magnetic field, and the other finger is current. And you typically use that when you're dealing with motors, right? So you'd pass a current through the coil, that would create a chain, that would create a magnetic field, and that would spin based on its reaction with the two permanent magnets on either side. Remember that?
yeah.
Right. Now, what happens when you have an induced magnetic field? Do you know about that? Are we going into territory that you don't know about? Do you know
Nah,
about Fleming's left-hand rule?
yeah.
Okay, you know about Fleming's left-hand rule, but do you know about Fleming's right-hand rule?
No.
Nah. So we have to cover that because it could come, apparently. So guys, I sent all my notes on the chat. Check out the physics manual. And let me advise you all which page to go to, since we're dealing with this particular topic. And like I said, Fleming's right-hand rule is not explicitly stated on the syllabus, so it's kind of strange that they brought this in this year, but we still have to cover it. So if we deal with magnetics and electromagnetism, I would advise you all to go to page. It starts at page 91. So go to page 91. And if at any time you don't understand something, feel free to unmute and let me know. Right? So Justin, just get ready to put your camera on because I'll have to show you how to do Fleming's right hand rule. Okay?
Yeah.
So give the question a read for me.
Um, Figure 1 shows a copper rod moving through a uniform magnetic field. The symbol with the circle on the top represents the magnetic field coming out of the page. Each end of the rod is connected to leads that are connected to the ammeter, which measures the electrical current. The rod is only allowed to move in a horizontal direction, left to right, right to left, while in the magnetic field.
Right?
Part A. Draw an arrow on the rod to indicate the direction of the induced current when the rod moves to the left.
Okay, guys, a lot of you are probably very confused. Let me just explain the basic concept here. So it have this thing called Faraday's law, right? Faraday's law. And what does Faraday say? He says that if there's a change in magnetic field, there's an induced current. So what does that mean? So somebody that doesn't understand this, I'd like you to unmute. So Jaden, do you understand what I mean by change in magnetic field? Yes or no?
Not fully so.
Okay. So what's going on here is that you have magnetic fields coming out of the paper. So these things here, these are magnetic fields. It could either be caused by a magnet or electromagnet. So, and you know what's a magnet?
Yes, sir.
And you understand that magnets either attract or repulse each other.
Yes.
So you don't see it, but there's a magnetic field. That being said, aren't we moving the rod in the magnetic field? So there's a magnetic field here. You're not seeing it, but there is a magnetic field. And this is supposed to represent the magnetic field coming out of the paper. So if we're moving the rod, isn't the rod, so like you have the magnetic field and you're moving the rod in the magnetic field. So ain't you changing the position of the rod with respect to the magnetic field?
Yes, sir.
And so because it's changing the position of the rod, it's gonna cut the magnetic fields and it's gonna experience a change. And so by moving the rod left or right, you're going to induce a current in the rod. So let me write down Faraday's law real quick. So Justin, you understand what I'm saying? By moving the rod left or right, you are cutting the magnetic field, and as a result of cutting the magnetic field, you're going to generate a current. Yes or no? Justin, I need to be
Yeah.
honest with me. So Justin,
Yeah.
anytime you have a change in magnetic field, there's an induced current or an induced voltage. Right. Right. So the rate of change of magnetic flux is directly proportional to the induced current and EMF. Now, EMF means electromotive force, and it's a fancy way for saying voltage. All right. So Justin, I needed to put on the camera now. I needed to put on the camera, right? Let me see if CXC mash up. You're still looking human, that's good. So Justin, in this situation, you understand that by moving the rod back and forth, you're gonna generate a current. Yes or no? Okay. Now, anytime you're generating a current, we call that induced current. So if you're inducing a current, you're always going to use you're going to use Fleming's right hand rule. You have to use Fleming's right hand rule. You'll let me know as soon as you start seeing back the screen, right?
Yeah, I could see it now.
Okay, and Justin, if we're dealing with motors, right? We have to use the Fleming's right hand rule. Yes or no? Means what I'm saying, Fleming's left hand rule, right? And you're familiar with that one. You're familiar with that one. So let me show you how we're gonna do this. So I'm gonna put on my camera. If everybody could put on the camera, that would be good because it's like I need to see everybody for this one, right? I need to see how all you're doing, like I need to see how all you applying it to the question using your hand. So I'm gonna put on my camera too, right? All right, so Justin, anytime you have an induced current, you have to use Fleming's right hand rule. So I want you to put up your right hand. Put up your right hand. You sure that's your right hand? You sure? Okay, cool. So in Fleming's right hand rule, your thumb represents the motion, your second finger represents the magnetic field, whether it's moving in or out, and the last finger represents the current. So I'll write that down, right? Let me write that down. Right? So your thumb, right? So your thumb is in motion. And so Justin, what would the motion be in this particular question? How are you moving the rod? Tell me, how are we moving the rod?
Left to right, left to right, or right to left.
Exactly. I know it's sounding very hard, but I promise it. Just stay with me and it'll be easy. All right, so Justin. All right, so Justin and Ocean, let me see on the right hand. Pop on the right hand. Let me see on the right hand. Okay. Your thumb represents emotion. So in the question, they are saying that, Ocean, I see you raise your hand. Yeah, you raise your hand on the Zoom meeting too. Let me know if you have a question. Oh, yeah. So the thumb represents emotion. The other finger represents the magnetic field, and the third finger, the current. So in this question, we are saying now we're moving it to the left, to the left. So that being said, the motion is going to be to the left, right? The motion is going to be to the left. Now, the third finger is the current induced, and the second finger is the magnetic field. So Ocean and Justin, in this question, the magnetic field, is it going into the paper or is it coming out at you? What is happening here? I want somebody to tell me.
Coming out to me.
It's coming out to you. So which finger should be facing you? I want you to tell me that, Justin, which finger should be facing you?
The third finger, the middle finger.
No, the middle finger is current. They're
No,
saying
the second finger. Second finger should be facing you.
the second finger should be facing you. So if you do that, it's kind of hard to do, right? If you do that, if you take the second finger and the second finger is facing you, it's kind of hard to do, right? But oh god, it looked like I showed all the middle finger, right? So look what's going on, right? You can't do this because if you do Fleming's left hand rule like this, it's pointing this finger here. Your first finger is pointing to the right. So you need to do this. So let me explain what have to happen, right? Let me explain what have to happen. So your thumb is in motion. Your thumb is in motion. That is supposed to be pointing to the left direction, right? Your second finger is the magnetic field that needs to be coming out to you. And the last finger would give you the current. So I want somebody to tell me, when you apply it, right? When you apply it, it really hard to see, but when you apply it, what direction is the current going, up or down? Somebody tell me, what direction is the current going, up or down? So the third finger is current. What direction is my third finger pointing in? Somebody tell me, up or down? Up, right? So let me run this back one more time. One more time, right? So your first finger is in motion. In this question, you're moving your rod to the left. Your second finger is a magnetic field. The magnetic field has to be facing you. And the middle finger will tell you the direction of the current. So in this question, you're making sure your thumb is pointing to the left and your second finger is facing you. And automatically, you'll figure out what the current is. So let's run it back one more time. So my thumb needs to be pointing to the left. Thumb is to the left. My magnetic field has to be coming out to me. And when you do that, you realize that the third finger automatically point upwards. So, Ocean, you understand what I'm saying?
Yeah.
Justin, what about you?
Yeah,
Yeah, so Justin, when we do that, what direction is the current pointing in?
upwards.
Upwards. So what that means is when I'm drawing the direction of the current, I will do this. So it's upwards. And so this is how I will draw the current. Justin, yes or no? Let me know if you understand that.
Yeah.
Yeah? Okay. Jiron, I feel like you didn't understand that. I feel like you didn't understand that. I'll wait till let me know if you didn't understand it.
Yes, sir, I kind of understand, but you see when you're pointing your hand, my finger was pointing downwards.
All right, so you understand that your thumb has to be going to the left.
Yeah.
Your second finger needs to be coming out and pointing towards you. And automatically, the last finger would be pointing upwards if you follow those steps correctly. So watch.
Oh,
My
yeah.
thumb is to the left direction. My second finger is pointing towards me because the current is coming out of the paper. And automatically, you see that the direction of the current will be upwards. So what that means is you have the current is in an upwards direction. And if the current is in an upwards direction, you can now draw the arrows to point in your respective direction. So yes or no, we understand that?
Yes, sir. Yes, sir.
All right, Ocean and Justin, are you understand that? Okay, so why did we use Fleming's right hand rule? Could somebody tell me that? Why didn't I use Fleming's left hand rule? In this example, are we dealing with a motor? Are we dealing with a motor? Tell me, Justin, are we dealing with a motor in this case?
No.
No. What are we dealing with? Since you're moving the rod and you're generating a current, it's an induced current, right? Anytime you see induced current, it's always Fleming's right hand rule, not Fleming's left hand rule. So I just drew in the current. Ocean, you understand that? Ocean, yes or no? Let me know what's going on.
Yeah, I understand.
Okay, word. So name the rule used to determine the direction of the induced current. Again, look, they're saying induced current. So anytime you see induced current, Fleming's right hand rule. And Justin, I just now say it. What was the rule I used to figure out the direction of the current?
Fleming's right hand rule.
Right. All right, so you all can take off your cameras now. Right? Justin, you can leave your camera on. Justin, you can leave your camera on. Unfortunately, Ali, I'm not here to, to trouble you with the gill, you know what I mean? Right? So Justin, I would like you to read this question now. Read this question for me.
An experiment was performed to determine how the strength and the magnetic field affects the value of the induced current. Readings of the speed of movement and the rod and the induced current were obtained and recorded in the table 1.
All right, so let me go through this thing in an intuitive manner. Ocean, if we do not move the rod in the magnetic field, will the rod experience a change in magnetic field?
No,
No. So will there be an induced current or induced EMF?
no, sir.
No. So we know automatically that this graph has to start at 0, 0. Why am I saying that? So, Jidan, let me explain that, right, Jidan? You there?
Yes, sir.
So if the speed is 0, what does that mean? Are we moving the rod?
No, sir.
No. And if you're not moving the rod, will you get a voltage?
Nope.
No, you need to move the rod to get a voltage. And the greater the speed is, the higher the voltage. Can we see that? So if you look at 0.2, it was 0.275. And if you look at 0.7, it's 0.950. So, so the faster you move the rod, you'll experience a greater EMF. And that is because the rate of change of magnetic flux is directly proportional to the EMF induced. If you're not moving the rod, you will not get a voltage. All right? So Justin, tell me, how would I figure out the voltage here? Tell me, how would I figure out the voltage there? You would need to read this part to figure out that.
Given that the rod has a resistance of 25 ohms, using Ohm's law to complete table 1,
All right, what is Ohm's law?
calculating the induced EMF.
Tell me, what is Ohm's law?
Ohm's law is the amount of
Hey, Justin, you're letting me down, you know. Ohm's law is
yes,
V is equal to.
study physics in a while.
I see that, but the physics exam is
Yeah,
not in a while. The physics exam is like right there.
yeah.
So Ohm's law is V is equal to. Finish it.
IR.
Yes, V is equal to IR. And so if we know that the current, so we know that the current is 0.0045. And what is the resistance?
25 ohms.
25. So using these two pieces of information, can I find the voltage? Yes or no?
Yes.
Yes. So everybody, I want you to plug that into your calculator and let me know. Jadon, did you know that Ohm's law was V is equal to IR?
So you can repeat back.
Did you know that Ohm's law is V is equal to IR? Yes or no?
No, sir.
No? Okay, well, whatever I didn't know, make sure you know it after class. So you're taking notes on thing?
Yes, sir.
All right, wood. And I sent all the formulas as well. I sent all the formulas, so you're good. So,
Yes, sir.
here what you do now, I want you to plug that into your calculator to find for V. Anytime you have current and resistance, you could use V is equal to IR to find the voltage. So plug that into your calculator.
Yes, yes.
And Justin, you tell me what you get as well.
I guess 0.1125.
Right. Let's observe the amount of decimal spaces we are seeing. So Justin, how much decimal spaces you seeing? Like in the values they give us, how much decimal spaces are you seeing?
4.
I see in 3. The decimal
Huh?
spaces is after the point.
Oh, yeah.
Yeah. So we got the answer 0.1125. So if you round that off to the third decimal place, you're gonna get what?
0.113.
Right. 0.113. Ocean, you good with that? Yes or no?
Yes, sir.
Okay, word. So Ocean, since we did this row, I would like you to do the other row. Figure out the voltage for this row. Right? And Jaden, I'd like you to figure out the voltage for this row.
Right, so
I got 0.009.
0.009. No, that's not correct. So tell me where you plug into the calculator to work this out. Tell me, Ocean, what did you plug into the calculator there to get your answer?
I multiplied, well, asymmetric axis multiplied 0.4 by 0.0215. It's 25.
Okay, nah. Remind me, what is Ohm's law? What does Ohm's law state?
E is equal to IR.
Correct. So if we want to find voltage, it's the product of the current and the resistance. So this is not the current. This is the speed of the movement. What is the current? What is the current for this?
20.
Come on,
0.0215.
right? And what was the resistance that they gave?
0.0215.
Right? And what was the resistance?
25.
25, right? So yes, plug that into your calculator and you're,
25.
so plug this into your calculator and you're supposed to get your answer.
so yeah, 0.75.
0.53.
So round that off to three decimal places. So you're looking at the third decimal place 7, and the number after 7 is 5. So you round up. So that'll be 0.53.
0.538.
Correct.
0.538.
Nice. Gideon, you were telling what did you get from this row?
So I did yeah 0.75.
Let me tell you if that's correct. Yeah, you're correct. Good job. Right? That's simple. So just remember that V is equal to IR, the product of the current and the resistance. Awesome. So Justin, you're good, right? It's real easy. Yeah or no, Justin?
Yeah.
Okay, let's move on to the other part. So give part 2 a read.
Use the results from table 1 to plot the graph of incidence, EMF, V against the speed of the movement, U, ms to the minus 1. On the grid provided in Figure 2 on page 7, draw a line of best fit through the points.
All right, Justin. So we know that this graph had to start from the what? So we plot in voltage against movement. If you don't move the rod, you're gonna get a voltage?
No.
No. So this graph has to start at 0, 0. So you'll see that when we plot it, right? So we want to plot V versus U. Somebody tell me, what are we plotting on the y-axis? Anybody, what am I plotting on the y-axis? They're saying V against U. V
On
against,
the y-axis.
right, you're plotting V. So whatever comes first, so it's V versus U. So that means V is Y and X is U. So keep that in mind. That's the same scenario for all the questions. And don't forget to put the units either. So V is the EMF. So you're going to say EMF, comma, P, or EMF in brackets phi. And Justin, for the x-axis, it's U, comma, what? Or U, open bracket.
MS T minus 1.
Right. And we're expecting our graph to look something like this because this graph had a start at 0, 0. So let we actually start a plot, right? Let me actually start a plot. Right, so Justin, we need to come up with a suitable scale. Remember that on the y-axis is EMF, which is voltage. And over here, it's U, MS minus 1. So we have Y, let me make this a little smaller. So this is Y, and this is X. Yeah or no, Justin? Tell me, yeah or no?
Yeah.
Okay, when we are plotting points, it's always what first?
X value first.
Right, so the first point is going to be 0.0045, comma what?
0.113.
All right, Ocean, I would like you to tell me the second point I need to plot.
0.011, 0.275.
Correct, so you understand that is always X first, then Y. Right. Jadon, tell me the third point I need to plot.
0.0215, 0.538,
Right, and just tell me the rest one time while you're at it.
0.0270, 0.675, 0.0300, 0.75, 0.0380, 0.950.
Okay, so we need to come up with a suitable scale then. So Justin, I'd like you to help me with the scale, right? So Justin, if you look at the points, right? What is the biggest value for the y-axis? What is the biggest value on the y-axis, and what's the smallest value on the y-axis?
0.0380.
No. Everything here is the x-axis. And everything here is the y-axis. So I'm asking, what is the biggest value on the y-axis, and what's the smallest value on the y-axis?
Biggest value on the y-axis is 0.950.
So whatever scale we use, it must cover that maximum value. And what's the smallest value for y?
0.113. No, wait. No, 0.75.
No, you're good. Wouldn't 0.75 be 0.7?
Oh, no, it'll be 0.5. Yeah.
Yeah. All right, so let me figure out a suitable scale now. In physics, in case you didn't know, your graph must have a title. Your graph must take up more than half of the page you cannot use a scale that's a multiple of 3, and you must state the scale that you used to get your full 8 marks. All right? So, Justin, let me figure out a scale.
Yeah.
All right. So, what are you thinking to do? Tell me, do you know what you have to do, or like you want me to help you?
Nah, help me.
Help you?
Yeah.
How I want you to think about it is, and this come like 9 and this come like 1? Yeah or no?
Yeah.
Yeah. And so I needed to take up more than half of the page. So if I say every 1 centimeter is 1, would it take up half the page? Let me see.
No.
No. If I do that, it's gonna be like that. So what do you think I could do then? If 1 centimeter not working, what do you think I should do? What's the next best choice?
Use 2.
Use 2. So let me see how that working. And I want you to count, right? So we know that it's not really 1, right? It's actually 0.100. So this could be 0.100. And I want you to keep counting, right? So this could be what?
0.120. Oh, no,
Right. And so we're just gonna keep counting and see if it works out. So our graph, the scale we use for our graph must include the minimum and the maximum. Must. This will give students real trouble. So then this could be 0.300.
300.
Right, 0.300. This one will be
0.400. 0.500. 0.600. 0.700. 0.800. 0.900.
what do you think is after 0.900?
1.
1.00?
Yeah.
Yeah, that's correct. And Jalen, what do you think is after 1.000?
Well, 2.00.
No, 1.100. So Jalen, let me look at the scale we used, right? I said that every 2 centimeters was 0.100. So that would mean I would add 0.100. You understand how I get 0.200?
Yes, sir.
Okay, and after that would be 0.300. So over here now, we're gonna add 0.100. So I think you're seeing how we get in 1.100.
Yes, sir, I understand.
Okay, now the scale again is not easy to figure out the scale, but the advice I could give earlier, I want a little locate the lowest y value and the biggest y value and try a thing. So 0.113. So like Justin, you see how we have like 0.113 and 0.950?
Yeah.
Some people might get confused and they might want to put 0.113 and think there. You can't do that. When you're doing that, you're using flush values. So like we're really gonna look at this as 0.100, and we're really gonna look at this as we're gonna round it up. If you round up to 0.950, you're gonna get
1.00.
right. So when you're doing a scale, I would advise to do this. You're rounding up and you're rounding down to the nearest whole number. So 0.113, if I round that down, it'll be 0.100. If I round up 0.950, it'll be 1.000. So my advice is always round up. You're gonna round up the biggest value to the nearest whole number. And you're gonna round down, well, not to the whole number, yeah, because this is a decimal, but I think I'll get what I mean. Justin, you understand what I mean? Like I wouldn't say 0.113, I would say 0.100, because that's like a flush flush value. Justin, let me just say, let me just say,
If I now come back.
oh, let me just say I had 0.235. I will round that to what?
0.24.
Yeah, I guess I could say that. I guess I could say that. But I would say 0.200.
Or to get flush value.
Yeah, 0.200. So you're looking at the highest value for y and the lowest value for y. You're rounding up the highest value, you're rounding down the smallest value. And it must fit more than half of the graph page. And yeah, it is fitting more than half of the graph page. So Jadon, with that being said, let me figure out a scale for the x-axis now. Let me try to figure out a scale for the x-axis. So Jadon, where's the smallest value on the x-axis? What's the smallest value I had to plot?
0.1, well, 0.100, well, 1 point, well, that's not 0.113
Wait, let me check something out.
is
Wait, I make a little mistake. Yeah, I make a little mistake. Justin, you spot any mistake? I right now I'm plotting current versus the voltage. Yeah, I make a little mistake. In the graph, they wanted us to plot V versus U. So I really should have it really should have been U. So like 0.1. Okay, so Jidan, you'll get through easy, don't worry. So Jidan, you understand that in the graph you want to plot V versus U, right? V versus U.
yes, sir.
So is this V versus this U? So it really supposed to be this. That being said, is V versus U. So just remind me, Jaden, V will be the y-axis or the x-axis,
The Y, sir.
and U will be the x, right?
Yes, sir.
Okay, cool. So we're gonna put an x by that column, and we're gonna put a y by this column. So let me just give back the points. So the point's gonna be, I'm gonna start you off, right? So really supposed to be 0.1, 0.1, comma 0.113, and just tell me the rest like real fast.
0.2, 0.275, 0.4, 0.538, 0.5, 0.675, 0.6, 0.75, 0.7, 0.950.
Yeah, so yeah, you shouldn't have a problem with the scale for the x-axis. Shouldn't have a problem. So yeah, so tell me on the x-axis, what is the smallest value?
So 0.113,
No, this is the y-axis.
well 0.1,
0.1, and we have to go up to
0.100.
no, what? So this is we have an x value here, we have an x value here, 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 here. Out of all the x values, this is the smallest, what's the biggest x value?
0.7.
Correct. So we have to go from 0.1 to 0.7. So could you think of a scale that I could use to take up more than half of the graph page?
So each box will be like 0.5.
I think you mean to say 0.05 because that would work. Yeah, that would work.
Well, yeah. So
But I go on say every two blocks is 0.1. And you would just tell me that work, right? So what's after 0.1 then?
0.2,
Keep
0.
going.
0.3, 0.4, 0.5, 0.6, 0.7.
So like, if we look at the span of the graph, does it take up more than half the graph page?
Yes, sir.
So you think we're in a good position now?
Yeah.
Yeah, we're in a good position now. Before we move on, I always advise students to figure out what one of the smallest block is. Try to figure out what one of the smallest blocks is. So Ocean, if I wanted to figure out what one of the smallest blocks is, how would I do that? How would I figure out that? Do you know how
Or divide 0.10 by 10.
Right, because you have 10 small blocks making up the 0.100. And what would you get?
You would get 0.001, sorry.
Right. And Justin, if I wanted to figure out what one of the very small blocks is equal to on the x-axis, how would I do that?
One of these small blocks.
Yeah, one of these blocks.
You divide that by 5.
5? No. Justin, how much small blocks making up 0 to 0.1?
Oh, 10.
10. So you're gonna say 0.1 divided by 10.
Divided by 10.
What
Okay.
are you gonna get? What are you gonna get?
One.
So you get 0.0.
Yeah.
Okay, cool. So now we can actually start plotting. So Justin, let me do the first one. So 0.1, comma 0.113. Right. So 0.1, I should only a trick here. So if it helps you draw like a very light vertical line. And now we just had to locate the y value. So Justin, 0.113. 0.113. Justin, since we know that one
Yes.
small block is 0.010, what do you think this block would be?
0.01.
No. If this block is 0.010, you're going to add 0.010 to 0.100. And so that's going to be 0.1. Tell me, 0.1. So you have to add 0.010 to 0.100.
Right.
So
I
what
get 0.11.
0, right?
Yeah.
What do you think this could be?
Yeah, add 0.010 to 0.110.
Yeah, very good.
0.120.
Okay, and we want to get 0.113, right? Can you
Yeah.
recognize that 0.113 is in between 0.110 and 0.120?
Yeah.
Where that will be? Would I put it over here, somewhere over here, or would I put it somewhere over here?
Somewhere the second spot.
The second spot, right? Cool.
Yeah.
So that will be like somewhere right there at that point.
Yeah.
Right, so that's going to be, so again, you have it's 0.1 and then 0.113. So that's this point over here. So that point is going to be, we could say right here. Ocean, you understand that?
Yes, sir.
Okay, cool. So Ocean, you help me with the second point, right? So the second point is 0.2, comma 0.275. 0.2, 0.275. So if we know that one of these small blocks is 0.010 and we want to get 0.275, what's the minimum amount of small blocks you need to go up by to get 0.275? 0.275.
The minimum amount of small blocks to go up to 0. Oh, that will be 7.
7, correct? Because this could be 0.210, this could be 0.22, this will be 0.23, this will be 0.24, 0.25, 0.26, 0.27, and this could be 0.28. And so we want to get 0.275. So wouldn't that be between the 7 and the 8 mark?
Yes.
Yes.
That's it.
And so to plot that point is going to be 0.2 and 0.275 will be like right here. Yes or no? Let me know if you understand that. Wait,
Yes.
This could be 6, this could be 7, this could be 8. Yes, so it'll be right here. All right, so Jaden, I want you to help me with the other point, right?
Yes.
Don't get scared. I know it's looking very intimidating, but just have faith, you get through. So the other point is 0.4, comma.
Five, well, 0.53.
Okay. So 0.538, right?
Yes.
Okay. Wait. I'll just show you 0.538. Let me just check back that calculation one more time. 0.0215 by 25. Yeah, it is correct. Nice. Yeah. So 0.538. What is the least amount of small blocks you would need to go up to at least make 0.53? How much you done?
Well, 3, sir.
3, right? So this
Yes.
could be 0.51, this could be 0.52, this could be 0.53, this could be 0.54. Yeah or no? Let me know if you understand that.
Yes, sir.
And our answer is 3/8. So that'll be in between what?
In between 3 and 4.
In the middle or like a little higher up?
A little higher.
Right. So you see, not bad. So 0.4, that'll be right here. That was easy.
Yes, sir.
Let me do 0.675 now, one time. Justin, 0.675. What is the least amount of small blocks I would need to go up by to get 0.675? Justin, come on fast.
Sorry, my wife, I keep dropping. I'll come back on.
All right, so what is the least amount of small blocks I would need to go up by to get 0.675?
Um,
Remember,
6?
6? No, 7. Remember, each small block is 0.01. So this
Yeah.
could be 0.61, 0.62, 0.63. This could be 0.65. And so
Mm-hmm.
0.675 will be in between what and what?
Between those two.
Wait, so this could be 0.65. This could be 0.66,
Yeah.
67, right? 8. So where's going to be in between?
7 and 8.
7 and 8, right? So I would just,
Yeah.
I trust that everybody understand the concept now. So I'll just sketch the others fast and we'll draw the line. Right, so that is 0.5, 0.675, so 5. Right. We're right here. All right. The other point, the last point. No, we still have 2 more points. So 0.6, 0.75, 0.6, 0.75. Right, so 0.75 is right here. And then 0.7, 0.950. So 0.7, 0.950, that's going to be right here. Yeah, no, let me know if they're okay with plotting on a graph. In every
Yes, sir.
in every physics exam, you'll need to do this. Should be able to do this. Right, so now we do the best fit line. Remind me, guys, because of Faraday's law, we know that this graph has to start at what point? This graph has to start at what point? 0, 0, right? Because remember, if you don't move the rod, the voltage gonna be 0. Right? So that we know that it has to pass through 0, 0. So I'm gonna line up my ruler and I'm gonna do the best fit. Right. Justin, if you like this good?
I would say so.
Tell me, does that look good?
Yeah.
Everybody, does this look like a good best fit?
Yes, sir.
Yeah, this go work. This go work. This isn't bad. Ocean, you understand how I do that? So when we do in best fit, we want the line to pass through the most points, and we're looking out for any oddities. So you notice that the line passed through like 1, 2, 3, almost 4 points. So that would have meant that these 2 points like are outliers or possibly mistakes. Let me know if you understand that. Ocean, let me know if you go with that.
Yes, sir.
So Ocean, anytime you do a graph question, typically they ask you for what next. Once you do a line, they ask you for what? Starts with G.
Gradients.
It is asking for the gradient next. So Justin, I have a question. When we find the gradient, can we use the points that were given?
No, we had to find new points on the line.
Yeah, they have to find new points on the line, right? That being
Yeah.
said, we have a real easy point we could use. Remember, this graph had to start at 0, 0. So like the first point I go and think of is 0, 0. And let me try to figure out another point. So like I'm looking for a nice clean point. Okay, this looks like a nice clean point. So this point over here, somebody had to read it off for me. So this look like, what's the X value looking like? Somebody tell me, what's the X value looking like?
6.5.
Right? No, 0.65, right? So 0.65. And we need to figure out the Y value. So this, somebody tell me fast, right? So this, if this is 0.8, this would be 0. What?
0.850.
Right? And so from 0.850, we're going up how much blocks? How much small blocks are going up from 0.850?
2.
3. Check it out. 1, 2, 3. It's 3. Let's see that. Watch. 1, 2, 3. And so that'll be 0.880. So now that we have the points, we can actually find the gradient. Right? And look at what they're asking us in part 4. The gradient G is related to the length of the rod L by the equation G is equal to 4.3 L. So they're saying G is equal to 4.3 L. Okay. So to calculate the length, obviously, you need to find the gradient. So let's find the gradient. So the 2 points that I used was 0, 0, and it was 0.65, 0.880. So guys, does it necessarily matter which one I call x1, y1, and x2, y2? Does it matter which one I call x1, y1, and x2, y2?
No.
It does not matter. You'll get the same answer either way. But it's common practice to let the smaller one be x1, y1. So we could let this be x1, y1. We could let this be x2, y2. And if that's the case, let's find the gradient. So G would be equal to, what's the formula for gradient? The maths exam was here already. I had to know this. What was the formula for gradient?
y2 minus y1 over x2 minus x1.
Right. So y2 was 0.880 minus y1 was 0. X2 is 0.65, 0.65 minus 0. And so I want you to plug that into your calculator. And let me know what you're getting. So I'm getting 1.35. Is anybody else getting that? 1.35?
Yes, sir.
Okay. And in physics, right, you're not going to get full marks for that. You need to state the units for the axes. So Jadon, did you understand how I found gradient? Yes or no?
Yes, sir.
Okay. So Jadon, if that's the case, I need to recall what the units were on the y-axis. So on the y-axis, what was the units? On the y-axis, the unit was? What do we measure EMF in?
Voltage.
Right. So
Volt.
we're going to put a little V over here. And on the x-axis, what was the units?
Meters per second.
Right. So the units for this is V slash ms minus 1. Yeah or no? Let me know if I understand how I do that. Yeah or no? Let me know, guys.
Yes, sir, I understand.
Yeah.
And they're saying they want us to calculate the length of the rod, right? They want us to find L. And so they're saying G is equal to 4.3 L. So G is 1.35, we just found for that. And that's supposedly equal to 4.3 times the length. So now I need to find for length. So right now, I have L being multiplied by 4.3. So what would I have to do on both sides to find for L? So Jadon, what would I have to do on both sides to cancel off for the 4.3? Because I want to find for 1L.
Divide
Divide both sides by?
by 3. Oh,
Nah. What would I need to divide by to cancel off for this whole thing?
so
I promise it's really easy. I'll give you an example. If I had 3 over 3, 3 and 3 will cancel off. If I had like 9.7, I would say over 9.7 for it to cancel off complete. So what would I divide by? I'm Jadon, tell me.
I'm not too sure.
I promise it's like real simple. If you want to cancel off, you need to have the same thing on the top and the same thing in the bottom. You understand that if you have 3 over 3, the 3 and the 3 will cancel off, yes or no?
Yes, sir.
So on top, what I have?
4.3.
So what do you think I have to divide by?
4.3.
Yes, that's it.
Oh.
That's all. Because I had to cancel off now, so it had to be the same thing. So L is going to be equal to 1.35 over 4.3. So somebody plug that into your calculator and let me know what you're getting for that. You should be getting like 0.3 something. So Justin, you understand what I did there? I wanted to find for 1L, so I divide both sides by 4.3.
Yeah.
0.314.
Right. And typically in physics, if they do not state how much you round it off by, it's understood to be 2 decimal places. So like you would have gotten 0.1395, etc., etc. If you look at
Yes.
the second decimal place is 1, the number after 1 is not 5 or more, so you're gonna round down. So your final answer is gonna be 0.31. Yeah or no?
Yes, sir.
Right, and we need to put the units for length. In this question, let's look carefully. So notice they said that the speed was in what? What is that? MS-1. What is MS-1? How would I say that? Justin, how would I say MS-1? What are the units there? We have what two units?
MSC minus 1.
Okay, but M is what? What does M stand for?
Movement.
No, M stands for meters.
Oh,
And
meters per second. Meters and
yes,
seconds.
yes. And additionally, guys, what is the SI unit for length? What is the SI unit for length? What do we measure length in physics? Oh, sure, don't we measure length in meters in physics? Like in physics, anytime you're doing calculations, you need to make sure you have the SI units. So in physics, we measure length always in meters, right? So our final answer is 0.31 meters. Are you understand how to get the 4 marks? Yes or no?
Yes, sir.
Yes, sir.
Okay, word. And we didn't finish this, right? In physics, you need to have a title for your graph. So for the title, I'm going to say graph of, so this is a graph of induced EMF V against speed of movement, which is meters per second. Guys, if I forget this in the exam, let me just show you something would that could get any full marks, right? You could always just say EMF versus EMF V versus speed of movement. Yeah, I don't want to correct. So just take a note of that. So right after class, I'll be sending you recording and the solutions. So let's keep pushing. Right, so Justin, read part C.
The experiment shows that the increasing speed of movement can increase the induced EMF. Give one other factor which would increase the induced EMF in the rod.
Okay, what do you think? We think I could do the magnetic field to generate a greater EMF?
Um,
Think I'd use a stronger magnet or a weaker magnet?
Wrong.
Stronger, yeah, Justin. This is very similar to speakers, And you notice that the more high-end speakers and like the more powerful speakers are bigger magnets.
Yeah.
Why do you think that is? That they just do that so you can create a stronger magnetic field so that the speaker will be able to better perform. So anytime you want to increase EMF or induce voltage or induce current, you could either increase the magnetic field, so you can increase the magnetic field strength. So increase magnetic field strength, or you can increase the cross-sectional area of your rod. Ocean, let me understand why that will make sense. So Ocean, if we increase the size of the rod, and when you move the and you would have to move the rod less for you to cut the equivalent amount of magnetic flux. Let me say it in a simpler way. Right? If the rod is bigger, when you move the rod, more of the rod is going to experience a change in magnetic flux. And so it's going to generate a greater EMF. So Jadon, here what I'm saying, right, Jadon? If I make the rod bigger, when I move it, more of the rod is going to cut the magnetic field. And because it cuts any magnetic field, or because there's a change in magnetic field, the EMF is going to be more. Right? So you can either increase the magnetic field strength, or you can increase the cross-sectional area of your rod. Right. Okay. So
Excuse me, sir.
yes.
What if we were to increase the current? Would that also be a factor?
All right. I hear what you're saying, right? I hear what you're saying. But in this question, aren't we generating a current?
Yes, sir.
Yes or no? In this question, do we have a current as a source, or are you trying to generate current?
Trying to generate current.
Right. So the question here is what you have to do to, to result in an increase in current. This is a generator essentially. And so to increase the generated current, you could either use a stronger magnetic field or you could make your rod bigger. You understand in context of this question?
Yes, sir.
No, but here what you're saying, right? You talking about a motor.
Yes, sir. That's what it is.
You talking about a motor, which makes sense, right? Because the more current you pass through a coil, the greater the magnetic field is going to be, and so the greater the torque of the motor. But I want you to realize the difference. A motor, you pass a current through a coil, it generates a magnetic field, and that reacts to the two permanent magnets. But this is different because this is induced current. And again, just make the distinction. In induced current, you use Fleming's right hand rule. When you're dealing with motors, you use Fleming's left hand rule. So that clears up all the confusion.
Yes, sir, it does.
Okay, no problem. Right. So Jadon, let me do 2A. Do you know the principle of conservation of energy?
So, no, sir, I did.
Okay, so I come like you're learning thing from scratch there. Scratch here.
So, kind of is because the way how that school I went into, it wasn't too good.
Don't worry, don't worry. When you had children and thing and I open up my school, they go send them to the school, right? Yeah.
Yes, sir.
Right. So we'll just try to absorb as much as you could. Try to learn how much you could, right? So the principle of conservation of energy says that energy can neither be created nor destroyed. It can only be converted from one form to the other. So let me give you an example, Jadon. Um, when you put a hot pan or a hot or something that's hot on a surface, right? The energy doesn't get lost. The energy gets transferred to something. So for instance, that heat energy would get transferred to the surroundings. You're not going to lose the energy, it's just going to get converted from one form to the other. Yeah or no? Like, Gina, let me give you another example, right? If I hit something, do you know what kind of energy that is? If I hit something,
Yes, kinetic energy.
right? If I hit something, that's kinetic energy. And so if I hit something, let me just say I hit, I hit a ball. If I hit a ball, right? And some of the energy is gonna turn to sound energy because they're gonna hear it as sound.
Yes, sir.
And some of it might turn to heat energy as well, because if I hit something, there's friction and heat energy, of course. So
Yeah.
the conservation of energy says that energy can neither be created nor destroyed, only converted from one form to the next. Justin, did you know that? Please tell me you knew that.
Yeah.
Okay, good. And so now, Jadon, we need to look at momentum, right? So what exactly is momentum? And again, if you don't know, you're learning it for the first time here, and just make sure you remember it. So momentum is the quantity of motion that an object possesses, right? The quantity of motion an object possesses or has, right? Keeping it simple, right? So if you see momentum, that's just the amount of motion an object have. Simple, right? So, Jadon, momentum, how much motion the object have, right?
Yes.
Momentum, that is what momentum is. And how do we get momentum, right? Momentum is measured as a product of mass and velocity. So momentum P is given by mass times velocity. And if you want to figure out the SI units, it's quite simple. Telma, Jian, do you know the SI unit for mass? What do we measure mass in physics? Yeah or no? Tell me if you know what we just measure mass in. I want to take that as a no. So in physics, we always measure mass in kg.
Yes, no, my wasn't coming.
Oh, and what do we measure velocity in? Velocity is speed. You would have seen that in the previous question. What do we measure speed in? In meters per second, right? ms minus 1.
Yes.
So if they ask you for the SI units for momentum, it's just kg multiplied by ms minus 1. Kg ms minus 1. So Ocean, did you know that you could derive SI units quickly in the exam? Like you don't necessarily have to remember it. Once you know the base SI units, you could always just find the product of or quotient and you get your answer. Yeah or no?
Yes.
Okay, wait. Justin, you understand that mass is kg and velocity is ms minus 1. So I just multiply that and I get kg ms minus 1, right?
Yeah.
Okay, wait. Right. So Justin, give this a read.
Part B, figure 3 shows a girl throwing a shot put in a sporting competition. State the energy changes that takes place from the time the girl begins to exert a force on the shot put until the shot put hits the ground and stops moving.
Okay, Justin. So when she have the ball in she hand, what kind of energy is that? Just by her holding the ball in her hand, what kind of energy is that?
Potential.
Right. So we start off with potential, and then she throws it. She there's a change in energy, right? So she uses mechanical force to convert potential energy to what?
Kinetic energy.
So anytime we're dealing with a movement, it's always kinetic energy. And from the kinetic energy, if the ball hits the ground, would you hear it?
Yeah.
Yes, so we can say sound energy as well, because you will hear the ball hitting the ground. That's sound energy. So some of the energy gets lost as sound. Well, not lost. It just gets converted from sound. I mean to sound, right? So potential, kinetic, sound, and ocean. When the ball hits the ground, will there be friction involved?
Yes.
So if it hits the ground and there's friction, what kind of energy? So like the sound and the kinetic will get converted to anytime I have friction. There's what?
Heat energy.
Correct. Heat energy. Right? And guys, eventually the ball is gonna stop and it's gonna stay on the ground. So if it's staying on the ground, what kind of energy is that? Anytime something is at a resting position, it's always what?
Potential energy.
Right. So I'm just gonna draw a quick diagram, right? So that everybody will understand exactly what I'm talking about. So it starts off with her having the ball in her hand, and because the ball is in her hand and it wasn't thrown as yet, it starts off as potential energy. Right? Then the ball is in motion. The ball is right now, the ball, when she lets go of it, the ball is in the air. It's moving, right? It's moving through the wind. And so there's there's motion there, so that's kinetic energy. When the ball hits the ground, it'll make a loud thud, and so that's sound energy. And the ball is going to roll around, and eventually it's going to come to what kind of equilibrium? Let me hear, guys. Let me see how bad all is. If the ball roll around and it eventually settles, what kind of equilibrium that is? Is it unstable? Is it stable equilibrium? What kind of equilibrium that is? If the ball rolls and it eventually stays there, Justin, what kind of equilibrium that is? You had to know that.
Stable.
Yeah, that's stable equilibrium. Right? Anytime an object is not moving, it always possesses potential energy. So take a mental note of that. If you're holding an object, or if an object is on the ground, it has potential energy. And in brackets, we're gonna just put out as stable equilibrium. So Jaden, you're probably wondering what the hell is stable equilibrium? All stable equilibrium is so okay, after I throw the ball, it's gonna land on the ground and it's gonna stay there. So if it stays there, that's stable equilibrium because it stays there. Stable, stay there. I think it's I hope you see what I'm talking about. Right?
Yes, sir.
Cool. This is an example of unstable equilibrium. Because then at any given time, this ball could either roll here or here.
Yeah.
Yeah. All right. So that's the 3 marks there. Right? Ocean, I'm gonna call upon you to help me with this question. So give that question a read for me.
The mass of the shot put is 4 kilograms. The goal exerts a force on the shot put for 0.6 seconds. The speed of the shot put increases from 0 meters per second to 9 meters per second before it leaves the goal side. Calculate the momentum of the shot put leaving the goal side.
Okay. Ocean, by chance, are you from Trinidad?
Yes, sir.
Okay, which part you from? Which school you go to?
I'm from Grandy and I go to Swaha in the college.
Okay, great, great. I'm not sure how well you learn physics, but how I just teach physics is as soon as you're reading the question, you want to look for information that's given. So you see, they say mass of the shot put, I'm going to write down M is equal to 4 kg. And the next question I'm going to ask myself is it in SI units? Is 4 kg in SI units?
Yes, sir.
Okay, so that's good. Then they're giving us time. The time is 0.60 seconds. Is that in SI units for time?
Yes, sir.
Then they're saying it starts off from 0 to 9. So the initial velocity, which is the velocity it was at. It was 0 is u, and that's meters per second. So that's in the SI unit for speed. Then it increases to 9 meters per second. So that's the final velocity. Right? So we have u, we have v, all right, and we have time. That's sounding like we could find for what? Anytime you have initial, final, and time, we could find for.
Momentum.
Nah, that's not what I wanted to hear. I wanted to hear acceleration. And then you go use that. You gotta find for the acceleration. Jadon, do you know what acceleration is? I'm gonna explain it in a simple way. Do you know what acceleration is?
Yes, sir.
Okay, what's the formula for acceleration? Do you know?
Well, sir, is so now sir, I can like call it on my top of my head.
Okay, Jadon, let we understand it conceptually. To accelerate means to change your what? What are you changing when you accelerate?
Your speed,
Your speed. So you're changing your speed, and anytime you're changing something, everything changes with respect to what?
velocity,
No, time.
time. Yeah.
Think about that, time. So all acceleration is, it's it. Okay, so Jadon, if we wanted to measure acceleration, and I would want to know how fast and I would want to know how much must speed change by and how long it take to change.
Yes, sir.
So like acceleration tells you how fast you're changing your speed. So all acceleration is just a change in velocity, the change in velocity over the time taken. That is all. So I think you can remember that.
Yes.
Acceleration is a change in velocity over the time. And if we write any formula for that, it's the final velocity, v, minus the initial velocity, u, all over the time. Why do I need to find acceleration for this? Why is that necessary? Actually, I don't need to find acceleration for this, right? But you'll need it in the next couple questions. I just realized we need to find acceleration one time. Ocean, let me find the acceleration one time, even though they are not asking us for it in this particular question. We might need it later on. So Ocean, if I want to find the acceleration, what's the initial velocity? I mean, what's the final velocity? What's the
9
final?
meters per second. 9
Ocean,
meters per second.
Ocean, if we're not even using our formula, and you could look at this and see the change in velocity, and you could look at that and see that increase to 9.
Yes, sir.
Yeah, you don't need no fancy formula to see that. And where's the time?
0.6 seconds.
Right, so plug that into the calculator and tell me what you're getting for acceleration.
$15.
Right, and the units for acceleration is, what's the units for acceleration? I don't know why.
Meters per second squared.
Yeah, meters per second squared, right? So that'll be ms minus 2, right?
Yeah.
Right. So you can write it as ms minus 2 or meters per second squared, however you see fit.
Yes,
Ocean,
sir.
Ocean, you see, we answer a question without even knowing that. And we already answer part 2.
Yes, sir.
Yeah. So why saying is when you read any question, try to understand what's going on and try to understand the information given. Right? You didn't need acceleration for
Yes.
velocity. But as soon as I see initial and final velocity and time, I was thinking acceleration. So, Jadon, I did momentum with you, right? I did momentum with you. So I want you to remind me, what's the formula for momentum? P is equal to what? Come on, Jadon, you can do it. What's the formula for momentum? If you're having a hard time remembering
Yes.
the formulas, there is a formula sheet. Do you have the formula sheet at its end?
Yes, sir.
You're looking at,
So, I know.
you
No,
can,
sir, I know it.
you have it?
No, sir, but I remember it.
Yeah, the formula sheet on the chat, you have it. I send the formula sheet
Yes,
on.
I have it.
Okay, nice, nice. So you want to look at kinematics and dynamics, and you're looking at quantity slash law, and you're looking for momentum. Momentum is
Right.
equal to P is equal to
Mass
times,
times velocity.
right? What is the mass,
4 kg.
right? What is the velocity,
9 meters per second.
right? Guys, why would I not use 0? Jiran, why would it make sense and why would it not make any sense to use 0 meters per second?
Because they're not moving at all.
Exactly. Momentum means the object is in motion. And so the object is in motion. When the object is in motion, it's moving at a speed of 9 meters per second. So you need to use 9 meters per second because that's the speed at which the shot put is moving at. Moving momentum makes sense. Right? So that'll be 36. And the unit for momentum, don't get scared. What do we measure mass in, Jaden? You should know by now. Mass. Mass is measured in,
Kg.
right? And velocity,
Moment. Speed per second.
meter.
Meters per second.
Right. So this is the units. That's 2 marks. Was easy or hard?
No, so that was easy. That's why I was getting mixed up. Okay.
Don't worry, you'll get through eventually. And we already do this. They ask us for acceleration. Justin, remember, acceleration is just the change in velocity. So we start off at 0 and we at 9 now. So 0 to 9 is 9. And the time it took was 0.60. So that's our acceleration. I trust that everybody understand that. And the units for acceleration is meters per second squared. Let's find the average force exerted now. So Ocean, I'm going to call it back on the scene. I'd like you to tell me, how would I find force?
Force is equal to mass times acceleration, so it would be 4 kilograms by 9 acceleration, which is 9
Nah, the acceleration was,
is
remember, acceleration was 15.
yes, yes.
Yeah, not 9. 9 is velocity. Velocity and acceleration are two different things. So 4 by 15 is, that should be 60. And what is the SI unit?
Six meters.
Right, newtons, right? So we measure force in newtons. Awesome. Let's move on. So Justin, I'd like you to read question 3. Read question 3.
Yes, sir. Figure 4 shows a car on a sunny day in a Caribbean country. A tourist places sunshade inside the windows in the windscreen to reduce the temperature rise of the air inside the car. Part A. Which material, dull black, dull white, shiny black, shiny white, is most suitable for outer surface of the sunshade? Suggest your answer.
All right, Justin. So if we want, so Justin, do we want heat to get trapped in the car, or do we want heat to be reflected?
Reflected out of the car.
Exactly. Jadon, understand that logically. If you don't want the car to get hot inside, you don't want the heat energy to enter the car and stay. Make sense?
Yes, sir.
So you want to use a material that will reflect the light and the heat energy. So which material logically would reflect? Would it be the dull black,
The shiny black, sir.
the shiny black?
Yes, sir.
Okay, if you take the light in your phone and you shine it against something that's black, will it reflect the light
Oh, I didn't see shiny white. Right, shiny white.
shiny white? Yes, because guys, and Justin, and when you shine a light on something that's white, doesn't it reflect the light back at you?
Yeah.
Doesn't black absorb light? So,
Yep.
so black, it cannot be black because black absorbs light, and it wouldn't be dull white either because dull white is a matte surface. Matte surfaces, they absorb light and they absorb energy. So you'd want to use a shiny white, right? So I feel like a lot of physics is common sense, guys. Like you can think about it and you can figure out if it makes sense or not. Right. So shiny white should be used. Should be used. The purpose of the sunshade is to reflect. Okay, I'll go on to that just now. So the purpose of the sunshade is to prevent sun rays from entering the car. So heat would not get trapped inside. Right? A shiny white sunshade will reflect most of the rays um, from entering the car. All right, so Jadon, did I say anything here that did not make any sense? Or like this is like you feel like you could figure this out in the exam?
Yes, sir, I can figure this out.
Yeah, you can definitely figure this out. And while we on this topic, I would like to look at the greenhouse effect one time. So let me look at the greenhouse effect one time. You need to know what would happen with the long wavelengths, the short wavelengths of light. You need to know that. So I can cover that really, really fast. Um, Let me look for the notes. Just close it off. All right, so let me look at the greenhouse effect fast, right? Like real fast. Like real fast. So whether or not heat can penetrate the glass depends on the wavelength. Heat is mostly carried by infrared waves and some UV. Short wavelengths have higher frequencies and higher amounts of energy and therefore more penetrative ability than longer wavelengths. Right? So the waves lose energy as they reflect off surfaces. Therefore, the short wavelengths that were able to penetrate the glass cannot escape once they convert to long wavelengths. Jadon, let me explain what happened in there, right? So, Jadon, basically we're saying that short wavelengths have the ability to pass through the glass, right? And long wavelengths cannot. Yes or no? Let me understand that.
Yes, sir, I understand.
So, Justin, we're saying short wavelengths can pass through the glass and they have more energy. So, short wavelengths, more energy, can pass through the glass. Now, when the short wavelengths pass through the glass, they lose energy, and by losing energy, they become long wavelengths. And so when they go into the car, they can't escape, right? Because they become long wavelengths now. And so over time, the short wavelengths enter, they keep entering, they get trapped, and it builds up heat inside. Yes or no? You understand that?
Yes, sir.
All right, Justin, you understand that? You need to know this, huh? You need to
A
be
little bit, yeah.
a little bit.
Yeah. You can go through back.
Justin, okay, and Ocean, pay attention, right? Kirsten, you too. So what I'm saying is, I want to have Kira in class. Kira in class. Okay. So what I'm saying is, if you have a short wavelength, what does short wavelengths mean? So I can probably take a little note about it here. So short wavelengths, they have more energy and they have greater right. So short wavelengths have more energy and greater penetrative abilities. So Justin, what I'm saying is, if you have glass, only the short wavelengths will be able to pass through the glass. Yes or no? Let me know if you understand that.
Yeah.
But what I'm saying is, because the short wavelengths had to pass through the glass, it's going to lose some of the energy passing through the glass. And if it loses energy, it's going to turn to a what? A what type of wavelength?
A longer wavelength.
Right. And if it becomes a longer wavelength, what's going to happen is it's going to have less energy, but it's still going to be heat energy nonetheless, and it's going to have a weaker penetrative ability. So we're saying, right, Justin? I'm saying that
Mhm.
when the short wavelengths enter the car, it's going to lose energy and it's going to become longer wavelengths. And when it becomes a longer wavelength, can it now leave the car? Yes or no? Could it leave the
No,
car? Yes or no?
no.
No. And so if this keeps happening, remember, we're talking about UV rays, right? And UV rays carry the heat energy. And so over time, inside the car is going to get very hot because you have a bunch of short wavelengths entering the car and they can't leave, so the energy stays in the car. Makes sense? That's the greenhouse effect in a nutshell.
Yeah.
All right. Ocean, let me know if you understand what I'm saying. That's like a little brief overview of greenhouse effect.
Yes, I understood it.
Okay, nice. So let's look at 2024 now. Let's continue this. But you need to know that you need to know the greenhouse effect. For homework, I'm gonna give all it to do 2024 June. Yeah. And tomorrow in class, we could do 2024 June. Yeah, so read this question here from Justin and answer it fast. Quick movement.
Complete these scenarios below by inserting the word which best describes the main process of thermal energy transfer. Part 1. A girl goes for a walk on a cold day. She touches a iron gate that removes thermal energy from her hand. The energy is then transferred through the iron gate by
Okay, so Justin, she touched the gate. So there was physical contact. So what kind of transfer is that? Anytime you make physical contact.
mm,
Let me give you an example, right? If you rest a hot pot on a
uh,
counter, the counter does get cold or get warm.
one
Okay, what type of heat transfer is that?
specific.
What? No. Look,
Uh,
look at another example. Look at another example. If you place um a metal fork in hot soup, what has happened to the metal fork?
it's get hot.
True what? True what? It is do
Heat,
heat. It is do what to the heat? It starts with C. We're talking about
conduct heat.
exactly. I talk conduction. Conduction. That is what I wanted to hear. So anytime
Uh,
physical contact, anytime you see physical contact, it's conduction we're dealing with.
okay.
Yeah, so conduction. Gina, you think you'll be able to figure out that through common sense?
Yes, sir.
Right.
But
Yeah,
I
tell me.
wouldn't uh like the specific name for it, like conduction. I didn't really know. So now I know.
Now you know. So part two. The girl holds the sides of a cup containing a hot drink. Her hands gain thermal energy by what are you all seeing there? Are you all seeing an example of physical contact?
Yeah.
Yeah, so that's conduction immediately. Some farm workers light a fire. The girl warms her hands by the side of the fire. Her hands gain thermal energy by, is she directly sticking her hand in the fire? Yes or no?
No.
No. Jaden, is she sticking her hand in the fire?
No, sir.
No, she's not a sukunya, right? She's not a sukunya. Um, Ocean, she's not sticking her hand in the fire, so there's no physical contact. So the other types of thermal transfer, you have radiation and you have convection. So guys, when all your Trinidad is a hot place, right? And so they just feel hot, so they just feel warm.
Yes, sir.
Yeah. So and you just hear people saying that sun radiating real heat, boy. Have you ever heard that before? Jadon, you ever heard that before? Like people are saying like, damn, that sun real radiating heat.
Yes, sir.
Or like People go say this. Don't stand up by the microwave. You'll get cancer because of radiation.
Yeah.
I think I know what the answer is, right? Radiation. Radiation is the answer. Because anytime we're dealing with heat being transferred in the atmosphere, it's typically radiation. Convection deals with fluids and like water. When you boil water, the the hot the hot the hot water from the bottom rises to the top. It gets cooled, and you see it just keep going and going and going. That's convection. So obviously this is radiation, right? So in physics, you could think of common sense examples, and most likely you'd be correct. So the answer is radiation, right? More past papers we do oligosy convection. All right, Justin, what is specific latent heat of fusion of a substance? Anytime you say fusion, we're going from what state to what state? Fusion. What does fusion sound like? Does it sound like a liquid or solid? What does it sound like?
Gas.
A gas. I think you're talking about vaporization.
Fusion could be like water to ice.
Yeah, or vice versa, right? So fusion means um it means solid to liquid or liquid to solid. Yeah or no? Let me know if you understand that.
Yeah,
So
I
what is,
just
Yes,
mix
sir.
up the two of them.
you can't mix up the two of them because I'm asking that question, right? What does vaporization sound like? What does vaporization sound like?
Vapor, gas.
A gas, right? Yeah, gas. Vapor sounds like steam. So fusion deals with, like, example, go be like ice to water or water to ice. So ocean, remember it like that, right? Just remember fusion, it's sounding like you're fusing things together. So maybe it's solid, right? So when we talk about fusion, we're talking about solid to liquid or liquid to solid. We're talking about a change in state. A change in state. And let's go see why I'm stressing that out so much. And then vaporization sounds like vapor. So that dealing with like a liquid to a gas or a gas to a liquid, right? Okay. Justin, remind me, what does the term specific latent heat of fusion mean? Anytime you say specific, it must contain what? Justin, I remember we reading this real times, like we real read through this. We remember when he was doing thermo, we real read through this. So anytime you say specific, it must contain mass. Anytime you see specific, your definition must contain mass. So I will start you off, Justin. Specific latent heat of fusion is the amount of heat energy
Needed to change the
needed to.
temperature of a substance by 1 degree.
Nah, you're close, you're real close. You're missing the mass. Remember, mass is a specific. Needed to change how much kg?
1 kg of a substance by 1 degree or 1 degree Celsius.
Okay, now you're talking about um
No?
you're talking about heat capacity. Talking about heat capacity. Um, remember over here, right, Justin? We're dealing with a change in what? Over here, we're dealing with a change in what? Starts with S.
Substance,
Now, no substance. You're going from ice to water or water to ice. That's a change in what?
state,
Yeah. So you need to say is the amount of heat energy joules needed to change 1 kg of a substance from solid, an example is ice, to liquid water. And I'm gonna write this in bold. You need to include this, otherwise you're not gonna get 3 marks. You're gonna get like 2, right? Without changing its temperature. Right? Again, I all about teaching physics in a practical way. So, Ocean, when you take a ice, right? Let me just say you take a block of ice and you put it in a hot pan. Does the ice immediately turn to boiling water?
No, it turns to liquid first.
Exactly. It needs to change state first before the water could heat up. And to go from, to change the state, you would use latent heat of fusion formula. You'd use that. Right. Cool. Just remember this, please. Let's do an actual question now. So Justin, give that question a read for me.
Small pieces of ice at the temperature of 0 degrees Celsius are added to 0.35 kg of water. The initial temperature of the water is 24.5 degrees Celsius. The water loses 35,000 joules of thermal energy as the temperature of the water decreases to 0 degrees Celsius. Part 1. Calculate the specific heat capacity of water.
Okay. When we're dealing with specific heat capacity, is there a change in temperature? Remind me, what's the formula for specific heat capacity? Justin, you're scaring me, no? Specific heat capacity. E is equal to what? MC.
Delta theta.
What does delta theta mean?
The change in temperature.
Right. So I want to let you take a note of this like in red. So the formulas for latent fusion, and latent vaporization, they deal with a change in state. Anytime you see a change in state, you use this, right? These are change in state. No change in temperature. Jadon, you probably think that's confusing, right? Because like, how you could change the state without changing the temperature? And maybe a little confused about that.
Yes, sir.
Okay, so Jadon, if you're holding ice in your hand, or like let me just use the example with the ice in the pot. Jadon, wouldn't the ice first have to turn completely to water and then change to then the water could only it was only then the water could boil?
Yes, sir.
Okay. So what I'm saying is, so like let me explain this. So like you're gonna have a point where you reach 0 degrees Celsius and it's still ice. So here what I'm saying, right, Jadon? You're gonna have a point where it's 0 degrees Celsius and it's still ice to some degree. To make the final change, you would need to rearrange the atoms and the structure of the atoms to go from ice to water. Let me say that one more time. So Jadon, it come like a threshold, it come like you reach a point. So let me just say a reach. So like Jadon, do you understand that ice is like 0 degrees Celsius, right?
Yes, sir.
And so when you put it in a pan, it can be how hot? It'll immediately go to the temperature of the pan.
No.
No. So first, it is how to go from 0 degrees Celsius ice to 0 degrees Celsius water. So you just need heat to change the state. And it's only after you change it to water, then you can heat it up. So here I was saying again for the last time, you need to change ice to water before you heat up the water. And to change ice to water, you're not changing the temperature. The only thing that's changing is how you're rearranging the atoms. That's the only thing that's changing. So ice would have, well, it kind of special for water, but in ice, the atoms is be arranged in a tight, compact manner, as like hexagonal. And the heat, you would need heat to change that shape and to get water. So anytime you see latent fusion or latent vaporization, you're not changing temperature, right? There's no change in temperature, just change in state. Right, Justin, if you see specific heat capacity, what do I mean? There's a change in what?
Change in temperature,
But no change in?
state.
Right. Right. Right, so change in temperature and not the change in state. Oh, Sean, when you was now learning physics, you probably would have time confused. Like you probably would not know when to use both of them. But like, I hope you know for sure now. Like, I hope you understand. Anytime you see a change in temperature, specific heat capacity. Anytime you see a change in state, latent fusion and latent vaporization. Understand? Don't I have the both of them.
Yes, sir. I understand.
All right, so Justin, now we finally answer the question. So you have a small piece of ice. So the ice is originally at 0 degrees Celsius, and you're adding it to 0.35 kg of water. So Justin, and you're gonna need, so Justin, before anything, you'd have to convert the 0 degrees Celsius ice to 0 degrees Celsius water, and then then the water would rise to the 24.5 degrees Celsius. You don't know.
Yeah, yeah.
Just keep that in mind. The initial temperature of the water is 24.5 degrees Celsius. The water loses 35,000 joules of thermal energy as the temperature of the water decreases to 0 degrees Celsius. So Jadon, notice that. Jadon, you notice that they're saying the water decreases to 0 degrees Celsius. Are they saying that is ice, or is it still water?
It's still water.
Right. So you would need, so you understand, to make that jump from water to ice, you would need latent fusion. You're not changing the temperature, you're just changing state. Right? So Justin, now we answer this question, right? So Justin, you want me to figure out specific heat capacity, and that is given by C. So we want to find for C. That being said, if they want me to find for C, they're supposed to give us the energy. They were supposed to give us the,
Mhm.
and they're supposed to give us the change in temperature. Did they give us all of that?
Yes.
What was the energy?
35,000 joules.
What was the mass?
0.35 kg.
Do we know what C is?
No.
No, we don't know what C is. I'll leave it that blank. By the way, capital C is heat capacity. Common C is specific heat capacity. Keep that in mind. Right? What is the change in temperature? So
0 degrees Celsius to 24.5 degrees Celsius.
okay, yeah. So what is the change in temperature then? You went from 0 to 24.5. I mean,
24.5.
no. You went from 24.5 to 0. Here we're asking you. I'm not asking you for the sign, I'm asking you for the difference. So difference. What is the difference in temperature there? So like you went from 24.5 to 0. What's the difference between 24.5 and 0?
No, 24.5.
Yeah, 24.5. So that's going to be a change. The change is 24.5. Your change is 24.5. Ocean, you understand that you would have had to lose 24. You would have had to decrease the temperature by 24.5 to go to 0, right?
Yes, sir. I understand.
So the difference is 24.5. So here what? Let me just simplify this, right? So on the right hand side, everything here is being multiplied. So I want to let's put 0.35 by 24.5. Plug that into the calculator and let me know all again.
I got 8.575.
Wait again?
8.575.
8.575. Okay, 1 second.
Hmm?
I get to add somebody to the chat. Oh my God. Un momento. All right. All right, so now we continue. Could somebody verify that? And again, 8.575?
Yes, sir.
Okay. And that'll be by C. So Jiran, I think you should know by now. If I have 8.575 multiplied by C, how would I find for C?
Divided
I have to divide both sides by
8 8.575.
A. You understand it now?
Yes.
So somebody do that and tell me what you're getting. So you should get like 40 or something.
$4081.
Right? 0.63. And
Yeah.
that is correct, right? That is correct because we know that the specific heat capacity of water is typically 4,100 ocean, and we know that, and that's like one of the constants you had to know that specific heat capacity is 4,100 or it's 4,200, somewhere around that, 41 or 4,200, right? You're supposed to know that, and so this is very similar to that, so you're correct. Justin, remind me, what is the SI unit for specific heat capacity? So in the formula sheet, it have all the units one time. So right now we're dealing with thermodynamics, so that's on the second page.
All right, just now, let me check. Specific heat capacity.
That is joules per kg
Yeah,
Kelvin
joules per kg Kelvin.
or joules kg minus.
Joules to the kg minus 1. Yeah.
All right, so that's it. Now, some of you all would have done it like this. Because they're saying a loss in energy, some of you all might put minus 35,000. This is an alternative way to do it, but it's the same thing, right? It's the same exact thing. So the energy senses a loss. You could say minus 35,000. Then they will say 0.35. Then they will say by C. And then they're going to say, when you find and change is usually the final minus the initial. So that'll be 0 is the final minus 24.5. And so you'd end up with 0.35 C by minus 24.5. And it will work out the same, It will work out the same. But some people would have done this. Both are correct. So when you work it out, you'll get minus 8.575 C. You would divide both sides by minus 8.575. And you get the same answer. So yeah, you're going to get the same thing, 4081.63, because the negatives cancel off. Right? Cool. Let's keep pushing. Jaden, is there anything here you did not understand?
No, sir, I understand.
All right. Justin, let me do part two. So part two, Justin, mass of ice added to water if all the ice melts. Okay. So how will we do this, Justin? So we're talking about ice melting. When the ice is melting, it's going from ice to 0 degrees Celsius to water at Remember, Justin, when you're changing state, there's no change in temperature. So ice at 0 to water at
0.
right. Now they are giving us. So first of all, let me just write down the formula here. Clearly, you see latent heat of fusion. And again, we're going from ice to water. So you should know liquid to solid. I mean solid to liquid. So you should know latent heat of fusion. So the formula for that is E is equal to mL subscript F. Right? So let me see what they want me to find for. So Justin, in this question, they want me to find for what?
The mass of the ice.
So if they want me to find for mass, then what should have been given? The only unknown. So what should have been given?
The n no, the energy. Yeah, the energy.
Energy is supposed to be given. Well, it's supposed to be given.
The
What does LF mean?
diffusion.
Yeah, LF means the specific latent heat of fusion, right? So that was given. The energy, where are we gonna get the energy from? What is the energy?
35,000 joules.
All right, so we are going to say 35,000. Right, we do not know what M is, so I leave that blank. And I know that it was given the specific latent heat of fusion of ice is 3.3 by 10 to the power 5. And so Jadon is the same concept. I have mass multiplied by this. So if I wanted to find for mass, what would I have to do on both sides?
So divide.
I'm gonna divide by what? So I don't want anything to be by the M. So I have this whole thing being multiplied by the M. So I have to divide by what on both sides?
3,500
No. What?
or 3.3.
I want to cancel off this, right? I want to cancel off that. So I'm going to write that same thing back in the denominator. So you can cancel off with itself. So I'm going to write
So
3.3
3,
by 10 to
1.
the...
Yeah.
And so you're going to plug this into your calculator to find for mass. So do that, and let me know what you get for mass. Justin, I have real... Justin, I have something that... Okay, I'm sure what I have, right? Like, this is actually insane. Watch this. I have nothing to worry about when it comes to paper one. I'll show you why. So, like, this document contains all the possible paper ones for physics. Like all, and the answers there as well. So, yeah.
Because and most of it is repeat, right?
Yep. But this have all the possible questions. And like, I want to say all, like every single one. So like, this
Okay.
is this is like CXE question bank now. So like, once you learn like these off, like you're good. Like you're gonna get full marks for sure. So I will send this, sorry.
Yeah.
Right? Yeah, so Justin, what did you get for the mass? And give me the answer to 2DP.
I get hmm, I got a real long figure.
Supposed to be 0 point something. Make sure you're plugging in this into the calculator. Make sure you're plugging this into the calculator. Ocean, you have a Sharp or a Casio?
I've both, sir.
Okay, the Casio is supreme. Kind of biased, maybe a little bit. Right? So if all you have a sharp, let me show you what letter plug in, right? If it is that you have a sharp, you'll need to plug this in. So Justin, you will need to put the 35,000 in brackets and then put a divide sign and then put the 3.3 by 10 to the power 5 in brackets, right? That whole thing has to be in brackets. Whole thing.
Okay.
So when you do that, you're supposed to get 0 point something.
Because when I learned it in school, we teach it how to put it as the ABC button.
Yeah, you could use that, but it's the same thing, divide. Right? So
I guess 0.1060600606.
right, that is the answer you're supposed to get. If you round that off, you're gonna get 0.1,
12.
no, 1,
No, 11. Yeah, 11.
and remind me, guys, what is the SI unit for mass? What do we measure mass in physics?
EG.
Kilograms.
kg, right? So you're gonna slap on the kg there, and they're gonna say the 2 decimal places. Right. Let's move on. We nearly finished with the paper, guys. We nearly finished. We nearly finished. Physics is a short test. Like I explained every single thing in detail. Like I can imagine how fast we got finished if I was just speeding through the answers. Like, trust me, guys. I can finish the physics exam and relax. I can get a good sleep too.
You said in the solutions for this paper, right?
Yeah, of course, of course. How you mean? Send it out one time.
Right.
Right. So read 4A for me. Read 4A.
Um, Visible light, radio waves, X-ray, infrared. Um, what was that symbol like?
Okay, this is gamma radiation. With gamma.
Gamma radiation and ultraviolet radiation are types of electromagnetic waves. Name the electromagnetic waves in each of the following regions labeled A, B, C, D in the electromagnetic spectrum shown in Figure 5.
Right? So again, we know that this is gamma. So let me just take this chance to do a little crash course on this topic. Right? I'll take that chance to do that. Okay. Where was that? Here it is. Right. So how it is, so like how it is tell people to remember it is like rich men in Vegas use expensive gadgets. Yeah. Say it one more time, Justin. So like rich men in Vegas use expensive gadgets. I'll write it down. So I can take this down. So R for rich, M right. So Oshan, how did you learn it in school? Well, did you learn a specific acronym?
Sir, I don't remember learning this in school.
You didn't learn this in school?
I'm most likely, but I probably forgot.
Okay, I have to remember this, like for sure, for sure, for sure. Right? So when we're dealing with the electromagnetic spectrum, the different types of the different things you have in the different radiation types have in the electromagnetic spectrum. I have radio, you have microwave, infrared, visible, ultraviolet, X-ray, and gamma. So take a screenshot of this and send it on the chat. So it could be like right there for you to look at. Right? So Jaden, how I like to learn it is rich men in Vegas use expensive gadgets. R is radio, M is micro, I is infrared, V is ultraviolet. What's in V is visible, U is ultraviolet, X is X-ray, and G is gamma. Yeah.
Yes, sir.
Right, and take a picture of the acronym one time. Take a picture of the acronym so you don't forget it. All right. So Jadon, which one has the greatest frequency? Which one has the greatest frequency?
So gamma ray.
Gamma ray, right? So again, rich men in Vegas use expensive gadgets. And this is in order of increasing frequency. Which one is the smallest?
Radio.
Radio. A man say radio.
Yes, sir.
Now radio real big, you know. I'm ask that
Gamma.
it will make so much sense. Yes, gamma. It will make real sense. And how do you think the radio does work? Jadon, how do you think the radio does work? The radio works through radio waves. That's why we call it a radio. And would you want something with a small wavelength or a long wavelength? Remember, and you could use a radio almost anywhere.
Yes, sir.
So like when somebody broadcasts a radio signal and it travels a great distance,
Yeah.
you would want it to have a long what?
Alone radio wave.
A long wavelength. A long wavelength. And gamma, well, they should know gamma is dangerous because of radiation. The reason why it's dangerous is because it's very, very extremely small, and so it could pass through, your body and thing. And so, like gamma rays, when it passes through your body, it damages you on a cellular level because it breaks apart the structure of your proteins and all that. Right? Because it's so small. It's like on the atomic scale. Right? So I hope I remember that now. So think radio, right? When we're using radios, the wavelengths have to travel a large distance, so long wavelength. Gamma is very, very small because it can pass through anything and it's dangerous. So yeah or no, I'm gonna follow you okay with that.
Yes, sir.
All right, so let me answer the question now. So let me just recall what we just saw rich. Let me just recall what we just saw wrote, right? So we said that rich men, so Jadon, tell me, rich men in Vegas, rich men
in Vegas use expensive gadgets.
Right. And we know that R stands for radio waves. So it is radio. M stands for? It is using plenty for ramen. I don't know if microwaves. I is what?
Infrared.
Right. V is?
Visible.
U is?
Ultraviolet.
Justin, what does X stand for?
X-rays.
Right. And V, what does G stand for?
Gamma. Gamma rays.
Gamma.
Gamma. Cool. Which one is the smallest? Remind me, which one is the smallest?
Gamma will be smallest.
Gamma is the smallest, and it has the greatest or weakest. I mean, what's it? It has the largest or smallest frequency.
It has the smallest frequency.
No, gamma has the highest frequency. Yeah, gamma has the highest frequency. Gamma waves have the highest frequency in the order of 10 to the power 20. Yeah. Yeah, no, let me know if you're okay with that. Video okay with that? So,
Yes, sir. Just made a mistake.
that's okay. You're talking about the size, I think, by accident. So like, this isn't increasing frequency. And if we're talking about wavelength, this could be in order of increasing wavelength. So Jadon, obviously, which one have the longest wavelength?
Radio waves.
Radio waves, right? So let me ask that question automatically, because you saw boss now in this. You tempted to say this is radio end. You tempted to say this is radio end.
Yes, sir.
Okay, wait. Take your time. Let me work in reverse. So what's after gamma? According to the acronym here, Richmond and Vegas use expensive gadgets. Which one is after gamma?
X-ray.
Right? So this is supposed to be X-rays. What is after X-rays?
Ultraviolet.
Right? And then you see how it lining up? Watch. Gamma, X-rays, ultraviolet, V. See? So let me see if you can reach radio. Let me see if you will even reach radio. What is C? What is after visible light?
Infrared.
Infrared. And ocean was the last one. Do we quite reach radio? Ocean, let me know.
We reach microwaves. Microwaves.
Yeah, we wouldn't reach. We will never reach radio. So which one here have the greatest wavelength? The longest wavelength?
Microwave.
Yeah, microwave. And since if all they want to be like extra bad, like real bad, or they could probably say the wavelength. So microwave could be 10 to the power minus 2. Infrared will be 10 to the power, I think is minus 5. I will check it after. I think visible is like 10 to the power minus 6, I think. Ultraviolet is 10 to the power minus 8. X-rays is 10 to the power minus 10. And this last one is 10 to the power minus 12. So let me see how correct am I. Oh, the only mistake I make was I supposed to multiply visible by 0.5. But they shouldn't penalize you for that. It's just like extra stuff. Like if you want to be like real bad, because I don't think they're gonna expect you to know this. This is like kind of hard to remember, but yeah. So Justin, we label everything already. Tell me where's A, where's B, where's C, where's D?
A is X-rays.
Right?
B is ultraviolet. C is infrared. And D is microwaves.
Right. Awesome. So let's move on now. So Vid, help me with this question. So we want to state which sound wave parameters affect each of the following properties of a musical note. When we are talking about pitch, we're dealing with what?
The frequency.
Right. And frequency is measured in?
Hertz.
Right. And loudness is?
Amplitude.
Right. And the amplitude is typically measured in?
Sure, I don't know.
Okay, so amplitude is like how high or low it goes. Anytime we're talking about length or distance, we're talking about what? What's the SI unit for that?
Meters.
Justin, Jaden, and Ocean, in case I don't understand this, with Jaden, you into car audio, aren't you? You into music?
Yes, sir. Yes.
Look at Justin, look at our partner here. Ocean, you into car audio and music, aren't you?
No.
No? Okay, but it's not music, right?
Yes, sir.
And in common sense, like, and we should know that, okay, a high frequency, and the high frequency could be like a squeaky voice,
Yes, sir.
and like a low frequency could be like a deep voice. So like when we're talking about those aspects, we're talking about pitch, right? We're talking about pitch. Like how, like Jadon, and if somebody have like a real squeaky voice, it would be like, damn, that person have a high pitched voice.
Yes, sir. I have a high pitched voice.
You say you have a high pitch voice?
Yeah.
No, your voice is not high pitch. I've seen worse. I had to double spell in my class. I had to double take every time he talking. I had to look around. I was like, nah. And he had long hair too, so it didn't help it. Maybe he was going for something that I just didn't know about. But that's
So me along like you.
like me. Yeah,
Yeah.
I've very long hair as well. Right? So I hope everybody understand this. And guys, everybody who in the car audio, until you know about loudness, until you know about speakers and thing. So what does make a speaker move? And not an amplifier, an amp.
Yes, sir.
So loudness, think amp, amplifier, amplitude. Cool. Let's move on. So Vade, help me with question C.
A person standing 100 meters from a wall claps sounds in an echo 0.6 seconds later. Calculate the speed. Okay, that'll have to be, if you're going to the wall and back, then it'll have to be twice the distance. So that's 200 meters. You hear me, sir?
Yeah, that's correct. Nice and nice. And 200 over.
Okay, to find speed, there'll be distance over time. So there'll be 200 meters over 0.6 seconds.
Perfect. And that'll be 333.33 meters per second. Excellent. Yes, man. Nice. 4 marks for that, Vade. It's so easy just to pass physics.
Very easy.
Like, oh my God. Jadon, if you do understand why he's saying he's gonna multiply the distance by 2, I'm gonna draw a diagram, right? So you have a person here, right? Imagine they clap their hands, it would generate a sound wave, and the sound wave would hit the wall, and then it would bounce back like a ball.
Yes, sir. I know that.
So like the sound wave would hit the wall, and then it would come back to the person. How much distance does the sound wave have to travel?
So it had to travel back the same 100 meters.
Right. And if any or you forget the formula for speed, just remember the units, right? Like, okay, in the car, and we just measure speed in kilometers per hour.
Yes, sir.
And kilometers is not distance, and an hour is not time.
Yes, sir.
Or speed is equal to distance over time. Simple like that. So speed is equal, well, speed is commonness, right? Speed is equal to distance. Well, I keep writing in capital letters, boy. All letters common letters. Speed is equal to distance over time. Right? The distance we have to travel is 200. And the time we have to travel, what's it? The time it takes for you to clap and come back to you is 0.6. So plug that into the calculator and let me know what you're getting for speed. And the units, the SI unit for speed again is meters per second or m/s, which means meters per second too. Right? So what is 200 over 0.6?
Three hundred and 33.3 meters per second.
And Ocean, and that makes sense because like we know the speed of sound is approximately the same, right? And you know the speed of sound?
Yes,
Yeah, the speed of sound is like
yes, sir.
330, I think. Let me just verify that. Well, when I look on Google, it's saying 343. All right. Yeah, 343. 333 is very close to 343, so we're doing something right, of course. For sure. So that's how you get your answer. So, Justin, if you get a question like this, are you going to say 100 over 0.6? Justin, if you get a question like this, are you going to say 100 over 0.6? Just because 100 meters is the distance?
No.
No, you're better than that, right? You're better than that. The sound wave has to go to the wall and then back to you. All right. So, Justin, help me with this question.
Mm.
I know you like these. I know you like this topic.
No.
It's one of the hardest topics in physics. One of not really hard, but let's give people trouble. Right, so there we go. So give it a read.
Figure 6 shows a plane mirror AB. A ray of light strikes the mirror at point X with an angle of incidence I between 0 and 90 degrees. Complete the diagram to show the path of the incident ray and the corresponding reflected ray. Mark on the diagram the angle of incidence I and the angle of reflection R.
When you read that, you know what to do? Be honest with me. Be honest with me.
No.
No. Yeah, you're real confused. It's like, damn, I kind of cooked. Jadon, you would know what to do with this question?
Not at all.
Okay, I like the honesty, Ocean, you gonna know what to do? I feel like Vade, you know what to do. Right? Vade, you know what to do?
Critical angle. No.
Critical angle? No. Let me
No,
show
that would be critical angle. Maybe back to question. Point it there. The incidence rate.
So let me write down a couple things all you need to know, right?
I think that the reflected ray will go about, yeah, it will just reflect back to what will be a straight horizontal line in our perspective.
Yeah, that is true. So that is true. So Justin, Jadon, and Ocean, right? Listen to what happening. Listen to what happening. Figure 6 is a plane mirror. Guys, when you look in the mirror, and you just see yourself,
Yes, sir.
I have a question. If you have an angle here, let me just say this is a mirror, right? Wouldn't the angle be reflected back the same way as it was coming in?
Yes, sir.
What if I tell you that's exactly what happened in here? I know they're just having a hard time seeing it. So listen to this, right? In physics, you have a couple things to keep in mind when we're dealing with refraction, reflection, and this specific topic, optics. The normal, you need to know that the normal, right? The normal is always perpendicular to the boundary right? So let me understand what I'm saying, right? So I'm saying that the normal is always perpendicular to the boundary line slash plane. What the boundary line is, it's basically the line where you would have a change in mediums. So Jiran, do you know what I see? Do you know what I mean when I say a change in mediums? Yes or no?
No, sir.
All right. So Jiran, if there's a mirror, right? Over here gonna be what? Imagine you're in a room and you stand up in front of a mirror. You're standing up in what? It is air, right?
Yes, sir. The space.
The space is air, right? This is air.
Yes, sir.
Behind and the mirror is what? Behind the mirror is what?
Air too.
Air. No, glass.
Yeah.
What's a mirror made of?
Glass.
Right. So here I was saying, and in the middle, you would have a line between air and glass.
Yes, sir.
Isn't it true that both of them have different densities?
Yes.
Right. So I just gave you a prelude into Snell's law. So Snell's law says that anytime you go from one medium to the other medium, there's refraction. Since this is a mirror, there's no refraction, there's just reflection. Because then we understand that a mirror reflects the image, reflects the object. We know that, right?
Yes, sir.
Okay. And so this over here, that is you see how I write boundary line slash plane? That's the boundary line slash the plane. And so the normal is always perpendicular to that. So could somebody show me what perpendicular to that is other than Vade? Because Vade, I know you know how to get the answer. I know. You fine with this. You fine with this. Somebody else. If we know that this is the boundary line or the boundary plane, I want somebody to draw a line perpendicular to that. Jadon, do you know what perpendicular means? Some people just confuse perpendicular with parallel. But Jadon, let me know if you know what perpendicular means.
Yes, sir, like up and down.
Now, perpendicular means 90 degrees too. So like this is an example. So like, you think you'd be able to draw a line perpendicular to this?
So I think so.
All right. So a line perpendicular to that would be like 90 degrees still. So take a little chance there. Take a little chance. I give you 2 minutes. 2 minutes is too much. Take a minute and draw it fast, man. Fast,
Yes.
fast.
So it's not like something like this. This.
Now, based on what you draw, the angle between that and that looking like 90.
Nah, sir.
Nah. So the
I don't
angle
want.
that looking like 90. Yes or no?
Yes, sir.
Ocean, you understand that? Ocean, yes?
Yes.
So like you go with this, right?
Yes, sir.
All right, Justin. I need you to understand that the normal, which is what you measure the angular incidence and angular refraction with reference to, is always 90 degrees to the boundary plane. And the boundary plane is just the line which you change your median. So like Justin, can you see 90 over here?
Yeah,
Yeah. So you understand that is the boundary line, right? I mean not the
yeah,
boundary. That's not the boundary line. This is the boundary line. The boundary line separates the two mediums. So like this is air and this is glass. So this is the boundary line. You understand that this is the normal, right?
yeah.
Okay. And if you want, you could draw a little 90. Little 90. How about right now looking like 90? But it's 90. And so let me show you what happening, right? It's real simple. Like I swear to God, it's like extremely simple. Watch this, right? The angle of incidence is the angle that coming in. So this angle coming in here. And Jadon, here what I'm saying again, right? When we doing these topics, the angle is always measured with reference to the normal. Say, understand that this is the normal, right? That is the normal.
Yes, sir.
So what is the angle between the normal and the incident ray? Yeah, so what is the angle between the normal and the incident ray?
So it will be 90.
No. The 90 is between the boundary line and the normal. This is an incident ray. So try to figure it out. What's the angle between this and this? Are you seeing an angle? Justin, are you seeing an angle?
Yeah,
Right. So the angle is this. This is the angle.
it would be 45.
It could be any angle. Did they specify that it was 45?
No, well, I would assume because 90 and you divide by 2,
No,
then
it
45.
doesn't matter. It doesn't matter.
Okay.
Heck, this guy, I could have draw it like this, you know. I could have draw it like that if I wanted. You draw it however I want.
Okay.
Um, because we know that it is a mirror, it's gonna be reflected anyways. So this is the incident ray, right? And it's gonna be theta I. And when you're drawing it, when you're drawing the refracted ray, well, in this case, it's a reflected ray because it's the same. You need to make sure the angle looking like this about the same, right? And this could be theta R. You know, I'm gonna forget understand that. And the parallel statement, theta I is equal to theta R because it's a reflection, it's a mirror. We're dealing with a mirror. Jaden, you tell me if you don't understand what I'm saying.
Yes, I understand what you're saying now. From
All right. And there's another way you could draw it. Wade, do you know the other way you could draw it?
You mean like the Snell's law, the other way to draw it?
Yeah, there's another way you could draw it and still get it correct. Oh, by the way, guys, you need to call this the normal. This is the normal here. So you label that the normal. And if you want, you could say that this over here is the boundary line or the boundary plane. Yeah. So Wade, where's the other method? You know?
I'm not. No, give me a hint. So give me a hint.
Okay. If it's a mirror, right?
Yeah,
Enter angle. Yeah. But enter angle could also come in from this side.
that is true. Yes.
Yeah. So then what about the arrows?
Well, it will switch. The refracted ray will become the new incident, and the incident will become the new refracted. So the position of the arrows will be inverted.
Yes. That is it. That's it. So the only thing that's changing is that instead of getting an incident ray over here, we're getting it on the other side. So if you drew this, it was also correct. So you could say either one. Wait, which one you not draw?
Um, I really don't know. I really don't know. But when you originally asked me, I thought about the one on the right hand side.
Oh, okay, okay.
Sorry, the left hand side.
This one.
Yeah, the one thought about it like that, but it will still be correct.
Yeah, it don't matter. You're saying the same thing. So you're good, you're good. You're good regardless. Jadon, you understand what I'm saying, right? And you could look at them and you could look into a mirror from different sides or like different places. Like,
yes, sir, from different angles.
yeah, so if you look into the mirror here, this could become your new incident ray, right? And then this will become your new reflected ray. So I trust that all of us good, right? Ocean, is there anything you do not understand?
Can you repeat, sir?
Is there anything you don't fully understand here?
No, sir.
All right, cool. So let me move on, right? Okay, my favorite part, because I'm an electrical engineer, and this is electrical parts. Lovely. So Jadon, you want to be an electrical engineer, right? So I'll ask you to help me with this.
Yes, sir.
Jadon, what is alternating current? What does alternating current sound like?
Good, correct.
No. Direct. All currents is flow. Okay, what is alternate? When you hear alternate, what do you think of?
Like it circle the night and it's like
Like if I say I'm alternating between um my Samsung and my you know about phones and thing?
yes, sir.
Okay, wait. Well, I hate Samsung. I wouldn't use Samsung, right? Um, what if I alternating between my OnePlus and my Vivo? That means I'm switching between them, right?
Yes, sir.
You know what Vivo one thing?
Yes, sir.
What? Wait, look at what.
I, I want.
Say good Vivo? No way.
No, I didn't get the Vivo yet. I'll get it later the year.
Yeah, same. After C-Cycle, bye. I can answer the question.
This question here,
Yeah.
I know you know the answer. You wouldn't be gaining anything from this. When I stumble upon a very hard question, trust me, I'll call you. Don't worry.
Thank you.
Yeah. Like the question from I think 2018 or 2019 with Brucey Shark. You know what I'm talking about Brucey Shark? Ask me that. She remember Bruce.
I will mash it up, sir. I will destroy that.
Yeah. So tell me what is alternating current? Jadon, what is alternating current? Like, okay, so here I was saying, right? If I have a Vivo and a OnePlus and I switch in between them, if I alternating between them, and that means I'm switching.
Yes, sir. Back and forth.
Right. So alternating current means that direction of the current is switching periodically. That's what it means. So like the current switching back and forth. You understand what I mean?
Yes, sir.
Let me give you a little example now. So let me just say I have a circuit here. By the way, all you need to remember the conventional current flow and electron flow. Don't forget that. Please don't forget that. I feel like I'm gonna come this here. And they're gonna ask you to differentiate between conventional current flow in a diagram. I usually predict the physics papers good, surprisingly. Yeah. So let me just say we have this battery, right? These are plus. Real fat, buddy. Let's just say we have plus still fat. Yeah. All right, so let me look at let me show you. I'm gonna be dealing with conventional current flow, right? So if we have conventional current flow, current goes from where to where? Veda.
Positive to negative.
I'm just not gonna say I know you know the answer, give it to somebody else. So Jaron, conventional current flow, that means current goes from positive to negative, right?
Yes, sir.
So if I were to draw the direction of the current, I would draw this. And will this ever change, or will the current always go in this direction?
You're always going that direction.
Right, because it's a battery. And a battery is an example of a what kind of source? AC source or DC source?
AC.
DC.
Oh.
DC means direct current. Direct, like it does not change. Does the direction of the current change?
No, sir.
It is always going one direction. Let me show you what alternating current does look like. So Jaden, watching, right? Let me just say at 1 second, at 1 second, the current could be going like this, right? Right? Here I was saying at time 1 second, the current could be going in that direction, right? At t is equal to 1 second. Let me just say at t is equal to 2 seconds. In the second, look what's gonna happen, right? What happened into the direction of current?
It's changing.
So that is why we call it alternating current, because the current changes periodically. It changes direction periodically. Understand?
Yes, sir.
Right? So current changes direction periodically. You need to include that part, periodically. You need to. Because if I were to draw the graphs for AC and DC, this is what AC looks like. Jadon, you know the oscilloscope?
Not sure. I don't know.
You're sure you want to do electrical engineering? I'm not against it, but I want to make sure that's like what you want to do.
Yes, sir. It's just that this is my first time getting into all of this.
Okay, well, I find this so far like hard to understand or like it's surprisingly easy to understand.
It somewhat easy, so
Somewhat useful. Okay. So this is what alternating currents would look like, right? And so in alternating current, you're plotting voltage against time or current against time. So let me explain something, right? Let me just say that this is plus 5 volts. If I if I swap the terminal, if I swap the terminal, it's gonna become what volts? How much?
negative.
Negative 5 volts. And what will happen to the current?
It will switch direction.
Exactly. You're gonna switch direction. And so for our alternating current source, if you look at the voltage with respect to time, the voltage is changing as time changes. Here we're saying, Jaden. So like 1 minute the voltage could be positive, and the next minute the voltage could be negative. Make sense?
Yes, sir.
And you understand that if the voltage change in direction, I mean, what's it? If the polarity of the voltage switching, the direction of the current will also switch. So, Ocean, let me know if you understand that.
Yes, I understand.
Ocean, where you want to be when you like when you finish secondary school and thing? Where you want to be? Where's your plans after that?
I'm not sure. I just now want to be employed.
You know you want to be what?
I
Employed?
want to be employed.
Or you don't have like any like serious passions or anything. You just like you want to be doing something.
Yeah, yeah.
I understand. But it's important to find what you love, eh? Like from a young age, like make sure you like you know what you're about, what you want to do. So like this is what direct current would look like. Again, this is voltage and this is voltage and this is time. So Justin, let me just say it's 5 volts here. Justin, when the time is 1 second, where's the voltage?
5,
When the time is 100 seconds, where's the voltage?
5,
Where's a million seconds past 5, where's the voltage?
5. It'll change.
Battery might die though. The battery might die.
No,
but,
yeah.
but the voltage would not change. So all you need to know the VT graphs for from AC and DC current, right? So this is DC. This over here, this is DC. And this over here, this is AC. So Jadon, you think you understand what I'm saying now? Because watch. This is DC, right? So Jadon, when the time is 1 second, if I take a read off and the voltage is 5,
Yes, sir.
no matter what the time is, it'll always be 5. But over here now, let me just say that this is positive 5 and this is negative 5. So watch this. 1 minute is 5, next minute is no minus 5. You understand what I'm saying? So it's changing,
Yes, sir. I understand.
it's alternating. Right, Justin, I hope you're not alternating, you know what I'm talking about. Hey, Justin,
Nah, man, what are you talking about?
you don't know what I'm talking about? With the
Nah,
two phones,
nah, nah,
two different SIM cards.
nah.
Can I tell you, I cannot tell you. I see you know, I know what you're doing. I don't want
That's
that,
a good shot.
I don't want that kill.
Nah, it's a good shot.
Okay, right? So, Jalen, with that being said, let me write down the definitions, right? So, in AC, look what I'm gonna say, the direction of the current. Try to finish my sentence. In AC, the direction of the current Jade, I'm trying to finish it. So in alternating current, the direction of the current is what?
Switching, always switching.
So if you say that you'll get a mark, right? But we're gonna be specific here. In alternating current, the direction of the current switches periodically. It doesn't just switch randomly. It switches after a period of time, consistently. Understand what I'm saying? Like so like after 1 second it will switch, after another second it will switch. So that means periodically, right? Resulting in a sinusoidal waveform. So Jiran, don't get confused. Justin, don't get confused. Ocean, don't get confused. This is what I'm talking about. This is a sinusoidal wave, right? That's a sinusoidal wave, right? And why I think we just use this symbol to represent alternating current? Because alternating current is produce a sinusoidal waveform, right? So that's AC. Let's look at DC now. So, Jiran, tell me what's happening in DC. In DC,
In DC, the current does always stay the same.
you gotta see that a little differently. In direct current, the direction of the current,
Always remains the same.
yeah, I'll take that. The direction of the current always. I find like this was such an easy paper. Like genuinely. Like this 2024 January paper too was so easy. Tomorrow we're going to January. I mean we're going to June 2024. Which one was a little harder? A little harder. A little, not that much harder, a little harder, right? Yeah. Justin. Part B. Give part B a read.
A transformer is a device used for stepping up or stepping down AC voltages. Draw an electrical symbol for a transformer.
Right. I just do a little crash course on transformers, right? Transformers work on the principle of mutual what? Wait, I could ask you that question. Wait, transformers work on the principle of? Where is Wade when you need them the most?
Non-induction.
Yes, works on the principle of mutual induction.
Hello, sorry, mom was calling.
That wasn't a convenient time, you know. The one time I ask you, one,
She had no called me downstairs to show the haircut. Because as soon as I finish haircut, I join class.
oh,
Yeah.
so what I'm saying is a transformer works on the principle of mutual induction. Here what I'm saying, right? Anytime you pass a current through a wire, you have a magnetic field being generated around the wire. So Jaden, I want you to listen carefully. Justin, Ocean, listen to what I'm saying carefully, right? I'll do it in more detail when we're doing questions, but here what I'm saying. Anytime you pass a current through a wire, a magnetic field is generated around it. Now, Ocean, if I supply a direct current, will the magnetic field ever change direction?
No, it will stay constant.
So it'll be a constant magnetic field. Can a constant magnetic field induce a current? So Ocean, remember at the start, we said that to induce a current, there must be a change in magnetic field. So can a direct current generate in a waveform? Can a direct current result in an alternating magnetic field?
No, no, it can't.
No, it can't. So can we use direct current for a transformer? A transformer works on induction. So how a transformer does work? It is work by inducing a current. And to induce a current, you need a change in magnetic field. So can we use direct current for a transformer?
No, we can't.
No, you can't. They can ask that question or no. They could be like, why can't you use it? Why can't you use DC current in a transformer? If they ask that this year, that'll be crazy. Just mark my words. Like, remember I say that. Right? I'm Jidon. You understand why DC current can work with a transformer?
Yes, sir.
Let me just draw the symbol for a transformer and we'll see it clearer. So how a transformer does work is you have two coils, right? You have two coils. Um, So and Jadon, while we at it, here what I was saying, right? I was saying that anytime you pass a current through a wire, it is have what around the wire? What does have around the wire? Or what?
The rubber or
No.
like
A magnetic field.
oh yeah.
Anytime you pass a current through wire, okay, so like let me just say I hook this. So I have a piece of wire here, right? It's a wire. And I hook it up to a battery. Since I hook it up to a battery, around the wire, you're gonna have magnetic fields in a certain direction. But since the current is the same, but since for a battery, does the direction of the current change?
No sir.
No. So will the direction of the magnetic field change?
No.
No. And remember, from the first question, you need to have a change in magnetic field if you want to induce a current. Right? Remember, Jadon, if you want to induce a current or EMF into something, you need a change in magnetic field. If you don't have a change in magnetic field, then it wouldn't work. So, Jadon, can a battery induce a current?
No sir.
No, because it will not generate a change in magnetic field. But if we're talking about an alternating source, and in an alternating source, direction of the current is changed periodically.
Yes sir.
If the direction of the current changing, Justin, if the direction of the current changing, what would also change as a result?
Direction of the magnetic field.
Right, and so you would have a change in magnetic field, and that is how transformers work based on the principle of mutual induction. So watch this, right? Watch this. So you're gonna supply an alternating current to the primary, right? You're gonna have a change in magnetic field. So 1 minute it might be looking like that. Next minute it might be looking like that. Let me just draw it bigger. So I give you a little crash course on transformers one time. So Jadon, this coil has an alternating source hook up to it. So it's gonna have an alternating magnetic field. So 1 minute it might look like that. The next minute it might look like that, right? So Jadon, you understand that it have a chain. Because I hook up the first coil, we call it the primary coil. Since I hook up the primary coil to our alternating source, it's going to create a magnetic field that changes direction. Yes or no?
Yes sir.
And so this coil, what is coil going to experience? That coil come like it's experiencing a change in?
Magnetic field.
Right. And anytime you have a change in magnetic field, you have a what? That's an I.
Inducing current.
Yes. And that is how our transformers work. That is it. So that is literally it. But if you use a direct power source, the magnetic field will never change. And if it don't change, then the secondary coil is not going to experience a change in magnetic flux. And so it will never generate an induced current. Cool. So all you understand how a transformers work now. That's good. A transformer, it have two types of transformers. It have step-up transformers and it have step-down transformers. What do you all think step-up transformers do? Make a guess. What do you think step-up?
So
Step-up.
it'll raise the primary voltage and lower the secondary.
You say what you're not technically correct. Mark, that question be if
Yeah.
if I supplying 20, let me just say we have a increase factor of 10, right? 10. If I supplying 20 volts on the primary side, how much volts do you have on the secondary side?
We'll have less.
No, 200. This is a step-up example. A step-up transformer increases the voltage that you supply in the primary. That's what a step-up does. So V,
Oh, I thought it was lower in the secondary.
no, you could look it up. This is a step-up. Step up. A step-up increases the voltage. A step-down decreases the voltage. What you are talking about is the current. That's what you're talking about. If I increase the voltage, I will drop the current to maintain the same output power as the input power. Yeah or no? I don't know if you understand that.
Yeah, I guess so.
It don't sound like you understand that. Watch. If I have 20 volts here, let me just say I have 100 watts. Random. How do I calculate wattage?
Wattage is the voltage and the amps.
Current, right? V and I. Yeah. So if I have 20 volts here, how much current am I going to need to make 100?
5.
Okay. But if I increase the voltage to 200 volts, you think I can still have 5 amps?
Nope.
No, because where I getting that power from? If I pay in 100 watts, how am I going to possibly get 10,000 watts? So you understand that the current is going to decrease.
Yeah.
To figure out it's going to be 0.5. It's going to be 0.5. The new current is going to be 0.5 amps. Yeah. So I think that's where it was confusing. Right? But a step up is increase the voltage in the primary, and a step down is decrease the voltage. It's in the name.
Thank you.
Right. Right. So let me just answer the question quickly. So a step down, a step up increases the voltage. And a step down decreases voltage. Right. Just keep that in mind. We nearly finished. I'll try to move faster. So state 2 advantages of using alternating current instead of direct current. Right? So I'll put down the answer. So AC voltage can easily be converted. So Ocean, remember, and AC voltage, and I could use AC voltage in a transformer.
Yes, so it could be either step up or step down. Easily it could be converted to.
Right, but I wasn't talking to you. I know you understand it. Again, I will get
Oh, you weren't talking to me? Sorry,
Ah,
sir.
Jiran. I mean, no. I think I said Ocean. Ocean, is it?
Yes, sir.
So Ocean, what I'm saying, right, is we know that direct current can work for a transformer. So I can use DC current with a transformer. What is so special about a transformer is that I could either increase the voltage or I could decrease the voltage. And so if I have AC voltage, I could always raise the voltage or decrease the voltage at a moment's notice for convenience. Right? So it can easily be converted to different voltage levels.
Yeah.
Right? Part 2, AC voltage can easily be generated. So more cost effective. And the third reason, lowers heat production. Right? So I gave 3 reasons. You only have to say 2. Right? So these are the easiest ones to remember. Part 3. Oh, look the question here. So Ocean, let me see if you remember. Transformers work on the principle of mutual what?
They work on the principle of mutual induction.
Right. And you understand the reason why we call it induction is because they induce a current because of the alternating current. Nice.
Yes.
So Ocean, let me do this question here. A mobile charger contains a step-down transformer which converts the input of 220 volts to 5 volts. So really, see what I'm talking about? Step down
Yes, sir.
would take the input and lower it. So step up would do the opposite. Right.
Yeah.
So Ocean, what are the formulas you need to know when dealing with a transformer? You can check the formula sheets. Check the formula sheet on the electromagnetism and electronics. You should see equations for ideal transformers. It's the last set of equations.
Yes, sir. Um, NP over NS equals to VP over VS.
Right? For those who don't know, N stands for the, so like NP would be the number of turns in the primary. Number of turns in primary. So Ocean, if NP is number of turns in the primary, what that's be? Right? So
Wait, sir, could you repeat, please?
so what would NS mean? What would NS be?
Um,
So in a transformer, we have a primary winding, so NP. So NP stands for number of turns in the primary. So what do you think NS would be? The number of turns in the
turns in the secondary.
right. So let's write that down here. And I don't think I had to say what VP and VS is, right? And to know that VP is voltage in primary, VS is voltage in secondary.
Yes, sir.
All right, good. The other formula you need to know is
VP LP is equal to VSLS.
oh, that is I. That is I. Let me explain why, right? So, Ocean, if I given the transformer 100 watts, how much are gonna get out of the transformer?
100 watts.
Right. So the input power needs to be equal to the
Outputs.
right. So the input power needs to be equal to the output power. So Jadon, let me give you a good example, right? Where input power is equal to output power. If you study for your physics exam, your output gonna be and Jadon, if you study in your physics exam, your output gonna be what?
You'll pass.
You pass, right? You go
Yeah.
pass. Yeah. If you don't put in much input, your output wouldn't really be nice. All right, so and to calculate power, power is equal to VI. So the input power will be on the primary side. So that'll be VP IP is equal to VSIS. So the formula that I have to use for this question is actually this one, right? Because they're saying if the output current that flows into the mobile phone is 120 milliamps, calculate the input current from the AC supply. So let me just underline the information they gave me. They gave me the output current. So output current, that'll be what? Tell me, Jadon. That'll be IP or IS. Output current. The output is in the primary or the secondary winding.
Primary.
No, the primary is where you put it in.
So then secondary.
Right. So they gave us IP. I mean, what's saying they gave us IS, right? They gave us the secondary current, 120 milliamps. Ocean, can I work with 120 milliamps?
No, sir.
No, I need to convert it to the SI units, right? How am I going to convert that to SI units? What does milli mean? Milli means 10 to what power?
10 to the third power.
Let me just send a table for this. So you need to know the prefixes and suffixes in physics.
Wait, so it's 10 to the minus 3.
Right. Oh, you had to know that, eh? Anytime unless you like milli, deci, centi, all you need to be very careful, extremely careful. Because in physics, you have to work in SI units. You need to. So I'm going to convert 120 milliamps to 120 by 10 to the power minus 3 amps. So now I could use that. And so, Ocean, what other information we know? They're telling us the input is 220 volts. So that'll be what? VP or IP? What that'll be?
Um, uh, P,
I
VP.
VP, right? Because that's the input voltage. And so the input is on the primary side. And it converts it to 5 volts. So 5 volts again, now on the what side? The primary winding or the secondary winding,
Secondary.
right? So that's gonna be VS. So I'm gonna plug in all my pieces of information I was given. So VP is 220. I do not know what IP is. VS, my secondary voltage is 5. My secondary current is 120 by 10 to the power minus 3. So Jadon, I want to find for IP. Right now, IP is being multiplied by 220. What I had to do on both sides?
Divide by 220.
Yes, you see the correct thing this time. Watch. Bam. Cancel out it. Yeah. So plug that into the calculator, guys. I'm gonna know all again. So was a small answer. Yeah, so anybody get answer any calculator? I'll wait till. Jadon, Ocean, Fade, and again answer from anybody. What going on, guys? Ocean, you having trouble plugging this into the calculator?
No, sir. I got 600.
No, not wrong. Um, no, not wrong. Show me where you plug into the calculator. Send me a picture on the group chat.
Sir, I take it. I reset the calculator. All right.
Oh, I'll plug it back in for me. And you're using the sharp right now or your Casio?
I using the sharp right now.
How come you don't use the Casio?
Yes, sir.
No, but no. I'm not saying it's not bad or anything. But how come you don't use the Casio? The Casio real good. Like, let me show you why I say the Casio real good. If you have the Casio, use the Casio. Because watch. Yeah, look at that ocean. Exactly how I see it there. I can write that. I can plug it in my Casio. Exactly how I'm seeing it. So yeah, I would recommend to use the Casio. right? Jadon, you have a Casio or a sharp?
Sa
Yes, V, that's the correct answer. Nice. So yeah, well, Jadon, I should I get an answer from you a while now? You must share how to plug it into the Casio, you know how to plug it in.
So I plug it in the same way you put it, and I was getting the error. So that is
Send me a picture of what you plug in.
just now. So
All right. Ocean, you get the answer? I had to make sure they know how to use the calculator.
Yes, sir. I got 0.002727.
Okay, and in physics, we write our answers in standard form. So you'd have to write that in standard form. But what I'm saying is, the Casio gives you everything. Like, watch, check the picture I sent you. The Casio gives you the answer in standard form. Which Casio model you have?
FX991EX classic race.
Well, yes. How? Ocean, we go follow, you know. You have the proper equipment. You have the proper thing.
so that is the way I understand it. That is the way how I put it in.
Oh, I know why. Your bracket is by the -3. You need to put the bracket. You need to press the right button one more time, and you go see it come down. The the bracket now by the 10 to the power -3. So Ocean, I'm gonna show you how to plug it in into the Casio. I really want you to use the Casio because if you use the Casio, it'll make your life so much easier.
Oh yes, yeah.
Okay, we will. Right, so and you see how nice that is? You don't have to convert anything to standard form. Right? So that will be 2.73 by 10 to the power -3 amps. Right? So Ocean, just verify that you get an answer, right? Just make sure you get an answer. Right, let's move on. So Jadon, read part two for me.
Determine the power supplied by the secondary to state your answer in SI units.
Right, so we have to figure out power. Remember, what is power equal to? If you don't know it, tell me one time that I don't know it. If you know it, tell me. Because time passing by. You don't know.
That's
There's nothing wrong with that. Don't be ashamed. You're learning. P is equal to VI. Just after today, make sure you know it. Otherwise, then we have a problem. Right? So
oh,
P,
so yeah, wait, I know that. I thought I was wrong.
right? So but the specific formula here, if you want, you could so you know with the secondary, right? Secondary. So I could write PS is equal to VS IS. Is the same formula? No, I just choose to write a S. And so what was the voltage in the secondary? Tell me, Jadon, what was the voltage in the secondary? It wasn't the question. So the secondary will always be output,
35 volt.
right? 5 volts. And what is the current? in the secondary. The current in the secondary was 120 by 10 to the power minus 3, right? So I want you to plug that into your calculator and let me know what you're getting. Ocean, did you ever get the answer?
Yes, sir, I got it.
Okay, wood. That's good to hear. That's good to hear.
So I is 0.6.
Let me just verify that. That's all incorrect, by the way. Ocean. Yeah, Ocean, did you get the answer? 2.73 by 10 to the power minus 3. I didn't hear if you said anything.
Yes, sir, I got it.
Okay, wood. Right? Yeah, the 0.6 is correct here. So the power, that sounds like a very little bit of power, but down 0.6 watts. V, that's like the power them Apple chargers is used.
and that's so underpowered one time.
iPhone, so stupid, eh?
They just use like 5 watt chargers, but nowadays it's like 20 watts separately.
Yeah, but when you have people like Xiaomi and Redmi and OnePlus using like
20 watts, crazy charging,
yeah, and my battery life for my OnePlus is real good.
insane. I quick question: would you rather take the OnePlus 12 or the 13
I
for the Zoom?
and I don't have the OnePlus 13, so I can't say, but I don't have no problem with the 12. I love the 12. It's do everything I need to do. And it's real good. So
Yeah,
right.
I'll go with that too. Periscope.
Yeah. So next part. So Viet, now go ask for read part 3. Wait, before we move on. Look at this. Look how easy physics is now, guys. Watch. Power formula. P is equal to VI for 4 marks. Believe that? Like, damn. Crazy. Jadon, you just had to plug 5 by 120 and you gain 4 marks.
So the only thing is that that's how to remember everything, like all the formulas.
Okay, you want to know how I know how to use this formula? Watch. What do you ask me to find?
Oh,
And what was the information I had? Let me look at the question, right? And I have voltage and I have current for everything.
yes, sir.
Yeah. All right, so Viet, how am I going to do part 3?
If there was a 10% loss of power, calculate the actual power delivered to the secondary circuits. So you're taking off 10% of the initial. So it will be 6 by 10 to the power of negative 2 watts. Then power loss will be 0.6 by 10 to the power of minus 2. Then it will be P1 minus the power loss. And P2.
Wait, that's all I can do.
You would get something like 6 minus 0.6 by 10 to the power of minus 2 watts.
I feel like you're doing too much, but yeah, that'll be the answer. That'll give you the answer. Watch, right?
Do it in your head, sir.
And the formulas we use was the ideal formulas, right? So it is 0.
Yeah.
But is for these primary as well, right? Yeah or no?
Yeah.
Because this is the formula for ideal transformer, assuming no losses. And so if there's a 10% loss, how much of the actual power when I reach the output?
90%.
Yeah, so just 90% at 0.6 and you get your answer.
Down.
And that should be 0.54, I think. Just check our maths.
Yeah.
And obviously that's the same answer you get, but I mean it's real simple though. It's just real simple.
Oh, that's only 2 marks. Sorry. Dumb.
Yeah. So Jadon and Ocean here was saying, right? We use the ideal formulas for a transformer, which means that Ocean, and if the secondary power is 0.6 watts, and that means that is how much the transformer would I get in the primary as well.
Yes, sir.
And so if it have a 10% loss, how much percent actually getting to reach the output?
90%.
Right. So just you fully understand what I do there. I take it that you fully understand.
Yes, sir.
And Jadon, if you're losing 10%, that means you only had 90% at 0.6. So I trust I
Yes. I understand.
right? So we move on. We are in the last question now. The last question on that is it. So the cloud chamber is a device used to detect the 3 types of radioactive emissions, alpha, beta, and gamma. Figure 7 shows a cross-section of the 3 identical cloud chambers containing the different sources. So for this, you need to know how alpha, beta, and gamma does behave, right? So I'm going to show you the notes, right? I have a table comparing everything that I just need to take a picture of. I want to take a picture of this. Take a screenshot fast. So Vade, which one have the strongest ionizing power?
The alpha.
Alpha. So if you put a cloud chamber, then the alpha particles will be able to ionize with the thing that is alcohol or helium or something. Supposed to be here. Supposed to be here. Wait, right here. Okay, it's dry ice and isopropyl alcohol. So in the cloud chamber is created by setting up a petri dish with dry ice and isopropyl alcohol. So basically what has happened is the alpha particle could ionize the particles like the most. So it forms a strong trail, whereas beta and gamma, they are not good at ionizing. So the trails start to get weaker and weaker. That's basically it. So I'm gonna take a picture of this. You need to know this. Oh, and my prediction is this year you're gonna have to find binding energy and mass defect and thing. Or mass defect. You gotta find mass defect. Wait, don't you know is mass defect?
So I'm not sure, but isn't it something similar to like the decay, radioactive decay?
Yeah, so mass defect is the mass that you lose when you undergo decay. So that's like when you find the mass at the left hand side, the right hand side, you subtract it, and that is U.
Yeah.
And you plug that into E is equal to MC squared. I know how strong feeling that gonna come this year. So I want to make sure you learn that. Right? So alpha has the strongest ionization power. So guys, I just need to remember what it look like. So alpha will have strong trails like this. Right? Beta is going to have trails that are not so strong, but it's still there. Right? And gamma is going to have little squiggly lines because gamma is not good at ionizing. So the trails wouldn't be very potent. Okay, did you know the cloud chamber experiment?
The experiment itself, no, but I have seen people repeating the experiments.
Okay. So in case it asks you about the cloud chamber experiment, just remember the cloud chamber experiment. To do the cloud chamber experiment, I'm gonna write it down one time here so you don't forget. Cloud chamber experiment. You use a petri dish, a petri dish. So this is isopropyl alcohol and dry ice. Right, so you have that. So state 3 properties of gamma emissions. Right? So gamma emissions, we're talking about gamma. So number 1, gamma has the highest. Actually, I don't need to tell all of this. I'll take the screenshot of the table. Let me know. I'll take the screenshot of the table. Ocean,
Yes, sir.
take a screenshot.
Yes, sir.
All right, so tell me one property about gamma emissions. Gamma is given by this symbol over here. So gamma would be this. So give me one property.
Gamma. So you have a high frequency, high frequency electromagnetic wave.
Okay. So let me see if we're saying this correct. So the nature is a high frequency EM wave, right? The ionizing effect is weak, penetration strength is strong. Yeah, all of those are valid ones. See, so the first one you can say is a high frequency what? High frequency what wave? What does EM mean?
Electromagnetic wave.
Right. Because and there wasn't the electromagnetic spectrum, like the rich men in Vegas use expensive gadgets. Gadgets was gamma, right?
Mhm.
Right, part 2. Jadon, tell me a property of gamma waves. Right, Jadon, I'm not hearing you. Another property of gamma waves is that they travel at the speed of light. Gamma waves, because they are EM waves, right? So all electromagnetic waves travel at the speed of light. Where did you know that? And all EM waves travel at the speed of light?
All right, yes, sir, I put in chart.
Oh, okay.
I said travel at speed of light in a vacuum, the highest electromagnetic and the high penetration.
Nice. Cool. Right. So Jadon, I want you to help me with this question, right? This is the last question. And we would have done a whole past paper. Yeah. So Jadon, give us a read for me.
Yes, sir, sorry. Wow. Michael. Figure 8 shows the graph of the mass of a radioactive. So I can't really see that with
Isotope.
isotope against time elapsed.
So the main thing you had to know with these questions, you had to know that you had to know what half-life is. And half-life is very simple. All half-life is just simply the time it takes
This
for the activity or radioactive mass to be halved. Right, so let's check this question out, right? So determine the initial mass of the isotope. The initial mass would be at time is equal to what? Make a guess, Jadon. If we're talking about initial mass, at the initial mass, the time is what?
0.
Yeah. So we're gonna draw a line, or a vertical line at 0, and we're gonna see where it cuts in the y-axis. So that looking like over here, right?
Yes, sir.
If you ask me, that looking like 3 blocks. This is such a bad copy. Oh my God. Okay, it's not exactly 3. It's looking like it's in the middle. So like we first need to figure out what one of these small blocks is equal to. So Jadon, how much small blocks we have from 0 to 100?
5.
5, right? So that means 200 could be divided amongst 5 small blocks, and that means each small block would be equal to
40.
40, right? So this looking like so this could be 1,220. I mean, what's it? It's gonna be 1,240, 1,260, 1,280. Yes or no?
Yes, sir.
Now watch, right? They gave the mass in grams. So all the thing, so when they give the answer, you have to give the answer in what? Remember in physics, we only deal with SI units. So 1,280, we had to convert that to kilograms. So how am I gonna convert that to kilograms? How do I convert
Divide
grams?
by 1,000.
Right? So divide that by 1,000, and you get 1.28 kg. Right? Right. Calculate the average half-life of the radioactive isotope. Now, if I want to find half-life, I need to find at least more than one half-life and divide by the number of half-lives. So let's find the first half-life. So again, Jadon, half-life is the time it takes for the original to be halved. So what we start off with again? We start off with 1,280, right?
Yes, sir.
No, I make a mistake because watch, this will be 1,240. This could be 1,280, and this is 20 more, so that'll be 1,300. My bad, guys, my bad. It's gonna be,
Oh, yeah.
yeah, that'll be 1,300. 1,300, and that'll be 1.30. Right. And so what is half of 1,300? So what's half of 1,300?
Say again, you got that?
What is half? So half-life, we're trying to figure out how much time it would take for 1,300 to become halved. So we need to halve 1,300. It's half of 1,300. Half of 1,300.
650.
650. Okay.
So we're gonna go over to our axes, right? So where exactly would 650 be? So like this could be 640. So 650 might be somewhere here. Okay. All right. So Jada, now what you understand what I do, right? We're trying to figure out half-life, and half-life is the time it takes for something to become half of the original. So half of 1300 is 650. So I draw a horizontal line and I take a read off. So this looking like 14 here, right?
Yes, sir.
So to go from 1300 to 650, it take 14 hours. So that's my first half-life. Now, anytime they ask you for average, you need to find more than or equal to 2 half-lives, right? To find average, of course. You can't find average with 1. So then we find our second half-life. Right? So Ocean are going to call you to help more the second half-life. And Vade, you will help more the last half-life. Right? So Ocean, how am I going to find my next half-life?
Half of 650 would be 325.
So 320. Okay, if it's just going to be 3, wait, so just going to be 240, 280, 320, and so 325 will be like somewhere here. Yeah, agree?
Yes, sir.
Right, and we'll take a read off here. Our question is that going to be 27? Am I going to say 27?
Nope.
Ocean, were you going to say yes?
No, sir.
Ocean, answer was 27?
Yes, sir. Yeah, it looked like it was 7.
Nah, but that's wrong. You know why that's wrong? Let me ask you a question, Ocean. Check this, right? To get this, so we say that this is 325, right? So 325 is half of 600. So, Ocean, what are we assuming the mass is when we find 325? What was the mass before? So what was the
The
mass?
mass before was
650, right? How long it
Yeah.
take? 640.
14.
14, right?
What is hours?
Yeah, all hours.
14 hours.
So Ocean, the question I have for you is, since we start at 650 now, so we started at 650 now, how long it take to go from that is where let's do. So you gotta be very careful, right? Very careful. So what is the difference between 27 and 14?
14. 13.
Right? And Vade help me with the last half. Jadon, pay attention to this, eh? Pay real attention to this. It's not the answer was not 27. Be it as tempting, like it's not 27, it's 13. Because if it's now 650 and it take 14 hours to reach 650, and it will take another 13 hours to reach 325. Jadon, yeah or no? Have anything I want to re-explain?
Yes, I understand.
All right. Okay, Vade, your time to shine now. What next?
So you have to find how much time it takes for the radioactive atoms to decay. Half of 325. Now would be, I think, 162.5, something like that.
Yeah, 162.5.
Find out on the graph, draw a horizontal line, and see where that matches up. You go down from there and shit off your time it takes.
So for those who confuse, what?
Your T3 will be your T1. Well, it will be T3 equals to T1 plus T2 minus T3.
Or you could just say 27 minus whatever I get here.
Yeah, you just minus it.
Yeah. For those who confused with how I do this, right? So wait, explain this to them. So how much is one block? How much is one small block?
Like 40.
40, right? So this over here will be 160, and we want to get 162.5. So like that'll be a little above 160. Right? And if you take a read off here, again, 41, right?
Yeah, it will show 41.
All right. So Jadon, is he third half-life 41? Think carefully about what you're gonna say. Is the
No, sir, only 41.
we go be what we gotta do to find that?
Say one had to minus the, well, 27 by 41.
Right? And what would I get?
14.
Right? So nice. Good job, everybody. So to find, so I'm just write the half-lives here. So the first half-life was 14, the second half-life was 13, and the third half-life was 14 as well. So if we want to figure out the average half-life, T average, that's going to be equal to the sum of all the other half-lives. So the first time and a half plus the second. And Ocean, since we have 3 half-lives, we need to divide by what?
By 3.
Right? And so all we're gonna say 14 plus 13 plus 14 divided by 3. Right? Or they're gonna know what they're getting.
13.66. Well, it'll be 14.
Now I had to round it off to the 2 decimal places unless they didn't tell us to round it off. I mean, what I'm saying is they didn't specify how much to round it off by, right? You never see they specify to round it off to the nearest hour. So we're just gonna write it to 2 decimal places. So 13.67 hours. Or the safest way to write it, you can write it as a mixed number. That'll be 13 and 2/3 hours. Yeah or no? Let me know if you're okay with that. Anybody confused at all? Jian, you confused at all by anything I did?
No, sir.
No? Ocean, you're good, right?
Yes, sir.
And Ved, yeah, Ved, I'll show you good. Right, so none of this is hard. And 5 marks for that is ridiculous. Right, so Ved, let me do the last question. So give it a read.
The half-life of another radioactive nuclide. Wait, the half-life of another radioactive nuclide is 10 hours. Determine the fraction of this radioactive nuclide that remains after 30 hours. So, first half-life will just be half of whatever. Second half-life will be quarter. It's just basically 1/8.
Yes. So I'm gonna explain that fast. So imagine, so at 0 hours, you'll have the full thing. So 0 hour. So 0. So Jaden and Ocean are like, well, I'm gonna probably understand what I'm doing, right? Check this. So Ocean, at 0 hours, I would have the initial sample, right? I would have the initial sample. It would not have a decay back at all. Yes or no?
Yes, sir.
Right? And after 10 hours, I would multiply the initial quantity by what?
By 0.5.
Right? So
By a half.
right? Jadon, after so when I reach 10 hours and 10 hours pass again, we go multiply by,
By half? Oh,
right? And then we go multiply by a half again. So that being said, so it's just gonna be a half by a half by a half, and you're gonna get 1/8, right? A half by a half by a half. And so that'll be equal to 1/8. So the fraction that remains Oh, guys, I wouldn't advise writing the answer as decimal, because they literally ask you, determine the fraction. So, Ocean, you understand what I'm saying? Ocean, I don't know if you understand what I'm saying. They said determine the fraction. So, probably shouldn't write the answer as a decimal. Yeah or no?
Oh, yes,
Right?
understand.
So that's it. So, guys, how will you find 2024 January was? Like, will you feel like it manageable? Ocean, how you find it is?
So
Yeah, Vid?
honestly, when I saw that, I just felt like I was so anxious with physics until I saw that paper, and I was kind of vexed because like you could solve the paper with your eyes closed basically. So you could read the questions and you could solve everything right there. 2024, 2025, and I think Jan, so that was just so easy.
2025 Jan?
Yeah,
Send that,
that was
send that paper to me. I only have 2025 June. Right? Send that paper to me. We can try that tomorrow then. Yeah, Vid, you know.
still honestly, I don't think it really makes sense for that one, sir, because it really don't make sense for the 2025 January people.
All right. Question, Vid, you would answer this question correctly? Yeah or no? Or you would use Fleming's left hand rule?
Hold on, I have to read it.
I'll go save you the reading. Basically, you're inducing a current. You're moving your rod left or right, right? And because you're moving your rod in a magnetic field, you're gonna have a change in magnetic flux, and so you'll generate a current or EMF. And so this is not a case where you are supplying current, you're generating current. So you cannot use Fleming's left hand rule. Would you have used Fleming's left hand rule?
Nope.
You sure?
Yeah, I'm sure.
Okay. Yeah. So Jaden, how you find the physics was bad or good? Like how was?
I find it was good. Feel like
I like
from plenty things that I didn't really fully understand and didn't even know, and now I could probably do after this year.
well, I'm happy to hear that. I will send out people for them to do. Or they go try to do as much as they could for tomorrow. Right.
Yes.
Ocean are interested. How you find out about the physics crash course? I'm curious.
My mother found it. All right. I was in the art maths. I was in the art maths group chat, and for my class, and a student sent Zoom into your art maths crash course.
Oh, okay.
I found it.
How you find the AdMats marathon was like, you understand anything?
Yes, I understood most of it.
Okay, so how you find the AdMats exam was? I have it right here. Wait, let me get the AdMats exam.
Um,
So I have the AdMats exam here. Bringing back trauma here.
yeah.
You don't want to see it. You don't want to see it.
Uh,
Uh, oh, you get through this question by chance?
yeah, I think so.
This one was nice, because when you plot the graph, the point of intersection would have been the solution. Because when you say sine 2x is equal to cos 2x, it's come like you're saying the y value is equal to the y value. And at the point of intersection, the y values will be equal. So that was the answer for that. Or you could divide throughout by cos 2x, get tan 2x. That'll be kind of hard for the level. But yeah, you got through with these questions.
This one, no, not this
But when I tell you how easy this was, I watched. All you had to do was integrate between x is equal to 0 and x is equal to 3. So all you had to do was integrate x squared plus 2 with between 3 and 0. And you can do that?
Yeah, I didn't see it. I didn't see it.
Shucks. Well, I'm sure you still pass something, right? That's the most important thing. So yeah. So how you find the physics? How you find the physics crash courses so far?
I find this was a good paper.
I know it was a good paper.
I've had it, so no, I think I could have passed, but I think it's a really good paper. It's nothing too crazy, but
Yeah, I didn't want to give Ollie anything to kill Ollie the first day. I say like, let me just like ease Ollie into it. The only hard question here, or the question that would have tired up plenty of people was the first question. 90% of people would have do Fleming's left hand rule instead of Fleming's right hand rule. Yeah. You not using left hand rule too, right?
yeah, I think so.
Yeah or no?
Yeah,
Yeah. But now
what's
you know
that?
for induced current, you always use the right hand rule. Where your thumb is the motion, second finger is the magnetic field, and the last finger tells you the direction of the current. So that's it for class today.
Yeah,
I hope I'm gonna send everything one time. Right? Thanks for staying on. Best of luck later, everybody.
Bye. So
I
you have a
see.
question.
Yeah. Yeah, tell
So
me.
you would you crash your if I asked you to start over?
Yes. Oh,
Okay.
bye.
Bye, sir.